25 minutes? Okay, you know. Okay. I will start at exactly at 9. Okay, so waiting people coming.
All right, good morning. Just an announcement. Today is the ICTP colloquium at 4 o'clock by Michele. There will be a poster session and reception after that. Because of the bad weather, the poster session is going to take place outside here. And I think also the food's going to be served there as well. Regarding the poster presentations, there's poster prizes. There are 5 generous poster prizes. You will need to win it to understand how generous it is. So anyway, looking forward to it. Thanks.
Oh, people are outside. I know that. Okay, time's up, and now we start this today's session. My name is Xingao Gong from Fudan University, Shanghai, China. 40 years ago, almost 40 years ago, I was students here. Okay, and learned a lot from these meeting rooms and the CISA. Today, I'm very happy to chair this session. By the way, today is a special day in China, National Teachers' Day. So please accept my best regards to all the teachers in the world from China. Okay, and now we start this morning session. The first speaker is by Daniel Polino, and he's talking about he's got the catalysis and the industry conditions. Please, yeah.
Thank you for the presentation, and thank you for inviting me for being here and speaking in this conference. And I'm Daniela Polino. I've worked with Michele since 2013, and I think I am the second engineer he hired in his history of postdocs. The first one was Matteo Salvalaglio, and I think that because Matteo was so good, he decided, okay, I can trust engineers. I can hire another chemical engineer. However, jokes aside, I want to speak about heterogeneous catalysis, and I know that we have heard a lot about it from Umberto, from Luigi already, but today I will show you some other catalysts that are important for the energy transition. And in fact, catalysis is fundamental in this field, and in particular to shift from fossil-based fuels to renewable energy systems. We have that catalysts are important for hydrogen production, for ammonia synthesis and decomposition in the ammonia circular economy. It's important in the synthesis of methanol that is considered as a possible synthetic fuel. It's important in waste and biomass conversion, in the synthesis of synthetic fuels and methane. So, however, we have seen that heterogeneous catalysts are not as static as people in the community studying catalysts from a theoretical point of view consider so far. Actually, Spencer, who was an engineer and a surface scientist in ICI, which is a company that developed chemical synthesis processes and is important in the field of methanol synthesis in particular. Already in 1986, in this review article, stated that metal surfaces are not static, but are mobile. And this metal surface mobility is induced by either thermal energy, which can induce disordering, pre-roughening, faceting with increasing temperature above 1/3 of the melting temperature of the metal. You start seeing all these disordering steps. But, and this is true, especially for different facets of different surfaces. In particular on copper. Copper was one of the main metal that was studied, and it was observed that, for example, for the CO, the 100 was less mobile, for example, than the 110 surface. But not only thermal energy can induce mobility of the surface, also adsorbed species. And in fact, again, for copper, it was found that on the 211, this is an example, but there are also for other facets, when oxygen is adsorbed on the surface, the CO211 surface reconstructs, and it forms this other structure here. So, why it is important to understand the surface mobility? Because different surface structure display different catalytic activities. And this has been also found in the past, in the 70s, and what earned Ertel the Nobel is this work on iron for nitrogen dissociation, and he found that the 111 facet of iron can catalyze N2 dissociation, which is the first step in ammonia synthesis, much better than other facets that are more stable, like the 110. And in a following paper, Gabor Somorjai, another giant in catalyst, in the field of catalysis, discovered that the 111 surface is not only the facets that activates N2 dissociation, but it's also the one active in ammonia synthesis, because what he studied was ammonia synthesis in the condition of close to the industrial condition, let's say. And he did not only study the pure surfaces that are crystal surfaces, like the 111, the 100, and the 110 that Ertel studied, but extended this work also to the 211 surface, which has some common properties with the 111 surface. This surface displayed a similar activity to the 111 surface. And what he found is that both surfaces have these C7 sites that are these iron atoms that are coordinated by other 7 iron atoms. So surfaces, different surface structure display different catalytic properties, but more than that, there are different atomic environments that can display different catalytic properties. And for example, in this work by Calle Vallejo on copper, methanol desorption on copper, he found that bridges, corners and adatoms display different properties, different catalytic properties. But how we can account for dynamics in catalytic systems? And this we have extensively seen how to do it. Luigi and Umberto already showed us. Just to recap, we need to correlate surface dynamics that are relevant in long time and size scales with catalytic activity, which involves reactions. So we need the accuracy of ab initio and the relevant sizes, time scales that are given at least by a molecular dynamics simulation, all atoms molecular dynamics simulation. So how to bridge these two scales? We can use machine learning potentials and enhanced sampling techniques. And this is the strategy that, together with Luigi, we started developing first with reactions in condensed phase, like urea decomposition, and then we moved to catalysts. So now, let's focus on methanol synthesis today, and what is the enigma of copper zinc oxide alumina catalyst. So methanol synthesis is a process that has been developed since 1923. At the beginning, it was synthesized starting from CO and hydrogen to give methanol. And the first process was proposed by BASF, and the conditions were very harsh, so we have very high temperature, very high pressures. And the catalyst they used, it was based on zinc oxide on chromium oxide. And this is a picture of the first reactor that was installed and used. Then, in the 60s, there was a revolution in methanol synthesis that was thanks to the ICI community, where they developed a new catalyst based on copper and zinc oxide on alumina, and this allowed to have much lower temperature and lower pressure. And this is a picture of what it is, a catalyst. So it's a bunch of, I don't know, you could say that are like a small candies, licorice candies, but instead it's a catalyst. And the catalyst processes are not actually an easy process, like you have just this giant reactor and you put your catalyst and everything works. It's more complex than this because this catalyst actually, it's a catalyst precursor. It's in the oxided state. It needs to be first hydrogenated, so reduced to the metallic form. And this transforms the catalyst within the reactor during the operating condition. So this makes the experiments on catalysts of this type very difficult because we need actually the operating condition to understand how they work. And methanol synthesis is actually even a bit more complicated than for example, ammonia synthesis, because not only one reaction is important, is because it was discovered that the reaction involved is not only the CO plus hydrogen that produce methanol, but it's also CO2 that is important. And this is why this catalyst has been the subject of interest, renewed interest in the last years, because there is this push to find ways to convert CO2 into useful products. So, and the importance of CO2 in this process actually was found already, again, by the ICI people, when they discovered that including more CO2 in the feed gas, they could improve the methanol yield at the end. And there are also other aspects of the catalyst that make this even more complicated. So we have more than one reactions, at least 3 overall reactions. So CO that converts into methanol, CO2 that also converts into methanol, and there is this balance which is called the water gas shift reaction that converts CO2 into CO and vice versa, depending on the condition of concentration, pressure, and temperature. And not only this complexity we have, but we have also a very complex catalytic system, which is composed by copper, by zinc oxide, and alumina. And the role of copper and zinc oxide in this catalyst has been debated for a long, long time. So at first, the linear dependency of methanol production with copper surface area pointed that copper is the active part of the catalyst. However, it was found that it's not only copper that is active in this producing methanol, but it was found that also zinc oxide overlayer forms actually on top of the copper nanoparticles. So there are people that say, no, copper is the active part, no, zinc oxide is the active part, and but what really is what people can observe is that if you start only from copper, you can produce methanol, but with a low rate. If you start only with zinc oxide, you can still produce methanol, but with another low rate. If you combine them together, the production just rise up. And many different active sites for this reason have been proposed. So copper and for different part of the reaction, actually, mechanism. So we have copper surface, copper zinc alloy could be produced, the copper zinc oxide interface, or the zinc oxide surface. So in this very complex scenario, we decided to focus on the zinc oxide surface. Since we were when we started this project, the view was that this zinc oxide covers the all copper particles, so it's probably the active part. So we started studying methanol desorption kinetics on zinc oxide. And in collaboration with Professor Copperet in ETH Zurich, we decided that zinc oxide is the active part of that we could start with, let's say, because to start with already the interface was too much. We decided that starting with the simpler things, it was better. So we focused on zinc oxide, and we focused on this methanol desorption reaction that is considered one of the possible rate determining steps. So we have high temperature and pressure that can affect the zinc oxide surface dynamics and kinetics. So we decided to determine methanol desorption on the zinc oxide surface using the approach I've described before. So developing a neural network potential in combining molecular dynamics with metadynamics to get a first training set, then produce a neural network potential able to reproduce the dynamics of the surface and the dynamics of methanol desorption, and then iterate this process and get free energies and kinetics. So to start with, we decided to choose to study zinc oxide Wurtzite, and the orientation we chose are those that are found as stable in experimental condition. So these are the surfaces we focused on. So what we found is that the different surfaces display different activity toward methanol desorption. We found that the 0,0-1 surface has the weakest binding, so the methanol was able to adsorb and desorb very easily on the surface. Then the 1,10 surface showed the more rigidity and stability. So the binding of methanol to this surface was quite strong for the how the oxygen were, this zinc oxide and the oxygen are placed in this surface. And the 100 surface is very similar in free energy binding with the 110, while the 111 showed the highest binding free energy. So, and this was due to the fact that the 111 surface is between the four that we chose is the most unstable. It starts to move and to show defects, and on this surface, methanol can convert into a methoxy, so can decompose into this methoxy species and an H atom, and as a consequence, the resulting binding free energy is much, much higher. So this is the equilibrium, and these are the binding free energies. Then what we studied is the effect of water, because water, we have seen, it's one of the byproducts of methanol formation, and it's known to be a poison for the catalyst. So it was important for us to understand how water affected the desorption of methanol. And we observed that water can interact in different ways with methanol, depending on the zinc oxide facet. Why? Because water can change this mechanism of methanol desorption and adsorption mechanism, creating these intermediates where water is interacting with methanol in such a way that takes methanol down. So, for example, we observed that on the 0, 1 surface, which was the one we have seen before with the least, with a medium binding free energy, we observed that this interaction with the water on this surface is strong, and you can observe how the kinetics slow down by 2 orders of magnitude. The same happens on the 110 here, and you can see how adding more water molecules induce the formation of this cluster. So this interaction, these hydrogen bonds that are formed between the water adsorbed and methanol reduce the desorption kinetic rate of methanol. On the 1,1 surface, instead, we observe the opposite behavior. And in fact, you see that the rate without water is very, very low, but once we introduce water, the rate went up by 6 orders of magnitude. And this is because addition of water increased the concentration of hydrogen atoms on the surface, and this increased the formation of methanol and its desorption. Then we also observed the behavior of oxygen vacancies, because we have seen that in the experiments, actually the zinc oxide part that could be active is a amorphous zinc oxide surface, and oxygen defects can have a big role in affecting the methanol yield, and we thus started investigating how removing oxygens affects the kinetics of methanol desorption. So we started seeing what happens if we remove one oxygen from the surface, and we observed that depending on the surface, zinc oxide atoms had different behaviors. On the 110, for example, the zinc atoms tended to cluster to each other, with each other, and so to get closer to each other, while on other surfaces, like on the 0, 0, -1 and on the 1, 1, on the 1, 0, 0, the zinc atoms tended to increase their relative distance. And this also can affect methanol desorption kinetics. How? When we introduce methanol on these systems, we observe that methanol doesn't have a strong interaction when the zincs atoms are close to each other, so this should not affect methanol desorption. While when the zinc atoms increase their relative distance, we are creating a vacancy that where the oxygen atom of methanol just likes to fall into and binds strongly with these defects. So in these cases, methanol desorption gets strongly limited. So to conclude, we have different surfaces that are present on the surface of zinc oxide and are stable at the condition of methanol production, synthesis, and while the zinc oxide, the 111 surface is less stable. And we observed that the 0, 0, -1 zinc oxide surface exhibits the lower desorption barrier, while the 110 and the 100 show similar behavior and have a moderately larger methanol desorption barrier, while the 111 shows the highest desorption barrier. And this is because it spontaneously creates these defects that we have seen interact strongly with the methanol, breaking it into methoxy and hydrogen. We have observed that water strongly influences the desorption kinetics of methanol, and this changes with changing the surface. So when the desorption of methanol was easy on some surface, the presence of water decreased this rate of desorption, while when the desorption of methanol was very low, in the case of the 111, water increased the kinetics of desorption. And also the presence of defects has different behavior depending of the behavior of the zinc atoms on the surface and how the architecture of the surface is actually built. So this was the conclusions, and I want to thank my group, Professor Cooperet, with whom we collaborated on this project, and I want to thank Michele for the days I've been with him, and in all these pictures I found there is always an added member, which is this little one here, and this little one here, and a little one here, which is my son. And I remember when I got pregnant, one of the first people I told that I was waiting was Michele, because I was not in, it was a difficult position in that time, but I remember that Michele told me, no, don't worry, we figure out how to do things. And this allowed me to go on to build a career in science, which I didn't ever imagine that could be possible. And for this, I want to thank you, Michele, and happy birthday. Thank you.
Thank you. Thank you very much. Now we have a couple of minutes to questions, discussions.
Thanks, Daniela. Really cool stuff. So I have a couple of questions. So in the case of these desorption energies, it looks like that apart from, I think, one surface facet, the difference between the barrier and the binding energy, the desorption energy itself is not that large. So I was wondering if
you mean here?
Yes, like,
okay.
You know, like 63, 57, like it's not a
Yes, these two are quite
large,
similar.
Yeah.
These two are almost the same.
So I was wondering if you have ever tested to highlight the role of dynamics with like static calculations, these binding free energies.
Not yet, but we are in the process of doing it, because I think it's interesting to compare with this type of calculation and see how actually dynamics affects the binding. Yeah.
Okay. And the second question was on the role of defects.
Yeah.
So did you characterize these defects from like a electronic structure point of view? Could you tell us a little bit more?
It's in
process.
It's in process, and
Okay.
we are in process of doing this too. Yeah.
Okay. Okay. Great.
So thank you.
All right. Thank you.
Thank you for the talk. Can you remind me, is the 111 zinc oxide the polar surface?
No, not the 1-1. Yes.
Same.
No.
No. Yeah, because then it's forced to do a non-stoichiometric reconstruction, right? Mm-hmm. Well, it's a long time ago I looked at this.
So I just have a comment.
Yeah.
So you said it's so important, the dynamics and so on, but all the second part of your talk was just static calculations.
No, actually it was from dynamics calculation. I didn't show...
But this could be done also with static, isn't it? I mean, these are standard static calculations.
Well, what I've... here the kinetics were from dynamics.
Okay.
Yes. And also here are all kinetics desorption rates. Mm-hmm. And when I show you here the formation of this vacancy on the 100, actually if you just minimize the surface, you get these structures, so the zinc atoms tends to collapse together. But if when we started and give temperature to the system, then they started to grow up apart and show this different type of defect. So.
Okay, my comment was that before doing the dynamics, usually you really need the usual traditional approach in this field is that you have to do a lot of static calculation to screen a lot of possibilities and so on and so forth. And then you can start to understand, have a little bit, okay. So maybe all this screening of possibilities, the part where the people doing this automatization have to say something, isn't it?
Okay.
Yeah, very nice. So experimentally, what is known about the amount of water on this? Is it a monolayer? Are they isolated clusters of what?
Well, they don't know how the water is on the surface because they cannot detect in the operating condition. But it's not irrelevant because it's a product of the reaction. So when you produce methanol, you produce also water. So it's on the surface.
So nobody's done like SFG spectroscopy of these systems?
I don't know.
Okay.
I will check.
Okay. Begin.
A comment on the comment of Annabella. Can you tell me which experimentalist does the job that you said to do before doing the experiment? Okay, thank you.
Okay. Due to the time limits, I must stop. As they thank the speaker again. And Let's move to the second speaker, Marco Perescoli.
Okay.
Yeah, please.
Okay.
Yeah.
Yes. So thank you, Xingyao, for the introduction. And I would like to thank Ali, Elio, and all the members of the organizing committee for inviting me. It's obviously a great pleasure for me to be here to celebrate Michele. And today we'll present an activity that has been carried out in part in collaboration with Michele on the phase change material for electronic memories. I was a postdoc in the group of Michele in the mid-90s at the Max Planck Institute. And I must say that since then, all my career has been based on the application of methods that Michele has developed over the years and that I learned to use thanks to his mentorship and the collaboration with his group. And this is the first paper that I co-authored with Michele, with Elio, Paolo Fokker, and Guido Chiarotti on the Carparinello-Parinello-Laman method. At that time, I was in CISA. I had just finished my PhD with Elio in 1994, and in the fall 1994, I moved to Stuttgart with Michele, and this is my first paper with Michele in Stuttgart, in which we applied the Carparinello-Raman method to study ice at high pressure. So this is the past, but the most recent collaboration with Michele is on the phase change material for data storage. These materials are chalcogenide alloys. This is the prototypical compound, germanium 2, antimony 2, tellurium 5, GST225. Also the binary system is of interest. These materials are used since the 90s for optical data storage, the DVDs or the Blu-ray disc, and more recently in the electronic non-volatile memory, the phase change memory. So when we start working on this material in 2007, so nearly 20 years ago, these electronic memories were among the emerging memories, emerging novel memories, and now they are emerged, so they are already a commercial product, as we will see. And so both applications, the optical disk and the electronic memory, are based, so rely on a fast and reversible transformation between the amorphous and the crystalline phases due to heating, laser irradiation in the optical disk, and or Joule effect in the electronic memory. The two states of the system, so the two phases, amorphous and crystal, correspond to the two states of the memory that can be discriminated because they have different electronic properties. So roughly speaking, the amorphous is insulating, the crystal is metallic. To be more precise, the amorphous is an intrinsic semiconductor and the crystal is a degenerate semiconductor. And so there is a large difference in electronic properties, also a large difference in the reflectivity, which is exploited in the optical storage, and a change in the resistivity, electrical resistivity by 3 orders of magnitude, which is used in the electronic memory. So this is a SEM cross-section of one of the first devices fabricated in ST Microelectronics. This is a French-Italian company with a site close to Milan, and so we start working on this material because of a collaboration with this company close to Milan. And this is a sketch of the device, so there is a thin film of GST between two electrodes and a resistor, so a heater that provides the heat to transform here a small region close to the heater. So by applying a current pulse, it is possible to melt the crystal that then amorphizes due to the fast cooling, or it is possible to apply a longer and less intense pulse to recrystallize the amorphous phase. So this is the current voltage characteristic. The crystal has an ohmic behavior, so high current, so low resistivity. The amorphous has a low current, so high resistivity. And so this is the read operation, so the measurement of a resistance at low bias. So by applying instead a current pulse and high bias, this is the reset operation, so you melt the crystal and you generate the amorphous phase. And by applying instead a pulse at lower voltage, you recrystallize the amorphous phase. This is the set. That it is possible because there is a sort of dielectric breakdown in the amorphous phase above a threshold voltage, which is called Ovonic switch. So after Ovshinsky, who proposed this concept in the late 90s. So this is an old idea that turned into a product rather recently. So in 2017, Intel and Micro commercialized a memory card with high density based on phase change memories. In the so-called 3D cross-point technology. So it's a cross-point, so there are several memories stacked along the vertical directions. And we have been working for a while with Micron technology on the materials for these devices, in particular for the selector here. So the selector are other chalcogenide alloys that feature this Ovonic switch, but they do not crystallize. So they are used to drive the current to the memory. So you can still buy this memory on Amazon. This is called Dioptane. But for several reasons, these devices are no more in production since 2022. So this is somehow the past of PCMs. The future of PCM is in neuromorphic computing. So we have seen, so it is possible to induce the set of reset operation by applying a single current pulses, but it's also possible to apply several current pulses to induce a partial crystallization during the set, or to modulate the size of the amorphous dome during the reset. So in this way, it is possible to build intermediate, discrete, or even analogic resistance states that depend on the history of the current pulses that you have applied to the device. And this is a way to build artificial synapses. So a synapse, among other things, is a resistor whose conductance depends on the history of the current pulses that he has experienced. And artificial synapses are important in neuromorphic computing. And so it is possible, for instance, to use the crossbar geometry that we have seen to fabricate accelerators for the matrix vector multiplication. So the voltage is the input factor, so the input vector, so applied to the different rows. The matrix, where you store the information, are the synaptic waves, so which consist in the different resistance in the different memories, and the output is the current. So you can perform this matrix vector multiplication by hardware, which is useful for the inference in artificial deep neural networks. So, as you know, so you have to perform several of these linear operations for the inference. And so this is a way to accelerate by hardware this process. The IBM lab in Zurich is very active in this field, and this is the cover of a recent issue on Nature Electronics, in which they report on the development of a chip for the inference of a deep neural network made of PCMs. This is the future of PCMs. So the present is our memories embedded in microcontrollers. Because the PCMs are cheaper than the traditional flash technology based on silicon at and below this technological node. So last year, ST Microelectronics announced the production of a microcontroller at this technological node with PCMs inside. For this particular application, so the flagship GST225 that I mentioned is not suitable because so there is a fabrication step in the memory that requires the amorphous phase to be stable at higher temperature, and so GST225 has a too low crystallization temperature. So for this application in ST Microelectronics, they devised non-stoichiometric germanium-rich alloys that have an higher crystallization temperature, and the raise in the crystallization temperature is due to a complex crystallization process, so there is a phase separation with a segregation of germanium. And we have developed a machine learning potential to really simulate this complex process at the length and time scale of the real device. But today I will focus on our study of the flagship GST225 compound that we start studying in 2007 in collaboration with Michele. So we generated the first model of the amorphous phase of this material. And so this simulation of this size at that time were quite demanding. And so we accomplished this task by exploiting the second generation Caparinello molecular dynamics developed by Thomas Kuhn and by Michele. And this simulation provided a wealth of results on the structure of the amorphous phase, the origin of the resistivity and optical contrast between the two phases that are exploited in the device, and also information on the aging of the amorphous phase, which is also important for the operation of the device. But you know, so there are limitations in the DFT, and so still now it is very difficult to tackle by DFT molecular dynamics the crystallization process, which is a key functional feature for the operation of the device. As you all know, machine learning has now changed the game in our field, and I will show that by using a machine learning potential, we can simulate millions of atoms for several nanoseconds at the real-time scale and size of the device to simulate the full set operation. And to this goal, we leverage on our previous experience on the binary system. So in 2012, in collaboration with Jörg Behler, we generated a potential, neural network potential for this binary system by using the scheme developed by Jörg and Behler, and we applied this scheme to simulate nucleation and growth in the bulk, also in nanowires. And we also studied thermal transport in collaboration with Davide Donadio. This was probably the first paper in which machine learning potential were applied to compute thermal conductivity. For the GST225, we used the DeepMD instead package developed by Roberto Carr and Wayne Ani in Princeton. The potential was developed by Omar Abu El-Khair, who was a PhD student at that time, and Omar spent a few months in the group of Michele to learn how to use this code. And this is the database, which is rather large for this system because we have to simulate all the different phases and also the phase change. We used the CP2K code to generate the training database. So this is an example of the validation of the potential on the structural properties, pair correlation function, distribution of the bond angles, coordination numbers, so the agreement is good for the amorphous phase, but also for all the other phases. And we reproduce, obviously, also the dynamical properties, the diffusion coefficient, phonons, and then we tackle the simulation of the crystallization on a relatively small size for now. And so this system has a crystallization rate which is very high. So it is possible to see the spontaneous nucleation on the nanosecond time scale, and so the evolution in time of the radius of the crystalline nucleus that are roughly spherical. So we can compute the crystal growth velocity from this slope here. These are the data in red. Now, to bring the theoretical data closer to experiment, we had to add van der Waals interaction because the van der Waals interaction slow down the dynamics, and so the crystal growth velocity are lower. They are the blue dots, and the green curve are the experimental data obtained from differential scanning calorimetry. Now, it's very difficult to measure. These are very indirect measurements of this quantity, so it's so to extract this information from differential scanning calorimetry, which measures simply the heat transfer during the transformation, so several assumptions have to be made on the crystallization kinetics. And so our good agreement between theory and experiment provides somehow a validation. So all these assumptions made in the interpretation of the experimental results. But then, so by exploiting GPUs, we can scale up our simulation to the device scale, and we considered the so-called wall architecture, in which there is a semi-cylindrical dome of the amorphous phase embedded in the crystal. The crystal is not shown. There are the two electrodes. There is the heater. The heater provides the heat for the transformation. So self-heating due to the Joule effect in the transforming material is negligible in this geometry. And then there are the dielectrics, so surrounding the material on the bottom, on the top, and also around the heater. So this is our model. So a semi-cylindrical dome of the amorphous phase embedded in the crystal. The crystal is shown here in this view at the real size of the device. So 15 nanometers, so there are nearly 3 million atoms in this model. Now the surrounding material is mimicked by frozen amorphous phase. So we have just a potential for GST, not for the other materials, but the surrounding materials have obviously an higher thermostability. And then we applied to thermostat, so not a thermostat here, so a semi-cylindrical region to mimic the hot spot generated by the heater underneath, and then a cold thermostat on the top to mimic so the heat dissipation through the top electrode. So this is the movie of the simulation lasting a few nanoseconds. Let me see, you can see the movie? No, why not? I don't see the movie. Oops. Here it goes. As you see, most of the crystallized atoms comes from the interface, but there are also some nucleation inside the amorphous dome. But most of the crystallized atoms comes from the interface. That's because the presence of this inhomogeneous thermal field. So the hot spot is very hot, so it is not possible for the system to nucleate close to the hot spot. And so most of the recrystallization comes from the boundary. And now this material, GST225, is known to be a nucleation-driven material, which means that if you take the film, the nucleation is so fast that many nuclei form because they grow. So in the film, nucleation is dominating the process, but in the memory, due to the presence of this interface and due to the presence of this inhomogeneous field, so we have found that most of the crystallization comes from the interface. And so this is useful information for our colleagues in the companies for the electrothermal modeling of the device. Now, I mentioned that that we computed the crystal velocity as a function of temperature, and our data can be well fitted by a phenomenological formula, the Wilson-Frankel formula. So within classical nucleation theory, which is simply the product of the kinetic prefactor, the diffusion coefficient, and the thermodynamic factor, which contains the difference in the free energy between the liquid and the crystals, is the driving force for the crystallization. So zero melting and increasing by cooling. Also, the nucleation rate, as you know, depends on a kinetic prefactor, the diffusion coefficient, and the free energy term also includes the driving force for the crystallization, obviously. So to have an high crystal growth velocity and high nucleation rate, it is necessary to have an high atomic mobility, so an high kinetic prefactor at large supercooling, where the driving force for the crystallization is larger. And it's believed that phase change materials crystallize so fast because they are fragile liquid. So in the taxonomy introduced by Angel, so liquids are classified as strong or fragile depending on the behavior of the viscosity. So this is the log of the viscosity as a function of the reduced temperature. Tg is the glass transition. So 1 is the glass transition, 0 is high temperature above melting. So in a strong liquid, there is just a single Arrhenius behavior, so a single activation energy. In a fragile liquid, the viscosity is low, down to low temperature, and then there is a steep rise close to the glass transition to reach the value expected at the glass transition. So this with a shape often described by this super Arrhenius behavior. Now, in a fragile liquid, if you start from the amorphous phase here, and you heat up the system, so you cross the glass transition, but you can reach a region here where the fragility is low, which means the atomic mobility is high, but you are still sufficiently close to the glass transition, so high supercooling to have an high driving force for the crystallization. So silica is a typical strong liquid with a fragility index. So the fragility index is a quantification of the fragility, which is the slope here of this curve at the glass transition temperature. So silica is a strong liquid. The many organic systems are fragile. Phase change materials are inorganic, but they are fragile. Or at least they are believed to be fragile, because it's very difficult to measure the viscosity at the condition of the operation of the device. So in this region here, because the crystallization is very fast. So on the other hand, molecular dynamic simulation offers the possibility to compute independently the crystal glow velocity we have already seen, but also the diffusion coefficient and the viscosity, and that's what we have done. So we computed the viscosity from the standard Green-Kubo formula, still in a relatively small model. So the agreement with the experiment is good above the glass transition here. So these two different colors correspond to two different settings of the simulation. And this is the theoretical viscosity above and below the glass transition that can be fitted by a phenomenological formula, Maillega formula, which is a popular way to fit the viscosity in a fragile liquid that yields the fragility index and the glass transition. And the resulting value are again close to those extracted from differential scaling calorimetry in a very indirect manner. So in the differential scaling calorimetry, they simply extract the crystal glow velocity from which they deduce the viscosity under several assumptions. So again, the good agreement is a validation of the assumption made in the interpretation of the experimental data on the kinetics. We have the diffusion coefficient, and we assess the validity of the Stokes-Einstein relation. So this relation here between the diffusion coefficient and the viscosity. And we observe a breakdown of this relation at low temperature. And this breakdown further boosts the crystallization, because so somehow the diffusion coefficient is higher at low temperature than one would expect from the value of the viscosity, that it must be high to reach the value expected at the glass transition. So it is higher than one would obtain by applying the Stokes-Einstein relation. So if you plot this product, so this should be constant when the Stokes-Einstein relation is fulfilled. It is, so down to 700K, and then there is a breakdown. So there is a breakdown of the Stokes-Einstein relation, which in supercooled liquid is usually ascribed to the emergence of dynamical heterogeneity. So which means the formation of a spatially separated region in which atoms move faster or slower than the average. And so the argument is very simple. So if you assume that the Stokes-Einstein relation holds locally, then there is a breakdown globally if the distribution is not normal, because 1 over the average of the viscosity is different from the average of 1 over the viscosity in the presence of these heterogeneities. And we have visualized these heterogeneities as shown here. So red atoms are fast-moving, blue atoms are slow-moving. So there is clearly an enhancement of this segregation by decreasing temperature. This map are map of the dynamical propensity, so nothing else than the mean-square displacement, computing on a characteristic time, which is estimated independently from a 4-point correlation function. And this is a mean-square displacement average over an ensemble of trajectory in the so-called isoconfigurational analysis. So we take a simple snapshot in the liquid, so the same atomic configuration, and we generate an ensemble of trajectory by so assigning randomly the velocity at a given temperature. And then so we average the mean-square displacement over this ensemble of trajectory, and in this way we can establish correlation between the structure, so the position of the atoms, and the presence of these dynamical heterogeneities. Now, in the binary system, germanium telluride in the past, we found that the most mobile regions are due to the presence of an higher content of homopolar bonds. So germanium-germanium bonds apparently promotes the diffusion. In fact, germanium atoms diffuse faster than tellurium. These were the results from a neural network simulation. In GST, we have not found a correlation between the dynamical heterogeneity and the chemical heterogeneity, so to speak. But, so we have indication that there is a correlation between the dynamical heterogeneity and the particular environment of germanium atom. This is found by looking at the angular limited two-body correlation function. So this gives a distribution of the probability of finding a bond of length R1 and another bond with length R2 nearly axial, so within a small angle of 20 degrees in our case. So these are the map of this distribution for the two length, different temperature, and for the bulk, so average over all the system, and for the slow-moving atom and the fast-moving atom. Now, at low temperature, you see, so there is a difference. In particular, for the fast-moving atoms, there is an enhancement of this tail here, and which correspond to a distance which are too long to be a bond. So, but there are atoms just outside the first coordination shell that promote the diffusion. On the other hand, in the slow-moving atoms, there is a secondary peak here, which correspond to a shorter bond. So there is the formation of an alternation of short and long bond, so a sort of pile distortion, and the shorter bond are stronger, so they hinder the crystallization. So to conclude, I have to acknowledge the contribution of my co-workers. So Omar, who generated the potential in collaboration with Luigi and Michele, and the simulation have been performed by Omar, and by Simone and Rocco. Omar is now a postdoc in my group, funded by the Italian Research Center on HCP. And so in conclusion, I thank you for all your attention, and in particular, I thank Michele for this mentorship, friendship, and support over the years. So thanks a lot, Michele, and happy birthday.
Thank you. Thank you very much. We have a couple minutes for questions, comments.
A clarification. So when you have this hotspot at the interface, it's something you put by hand, or it develops naturally during the simulation?
No, the hotspot is put by hand, yes.
Okay.
So there is just a small region within the GST in which we fix the temperature, yes.
So, yeah. And then I have another comment more. So, are these the electronic properties of this material nothing to do with these topological things? The elements seems...
Antimony telluride is topological. GST225 is not topological in the crystal structure of relevance for the operation, because the amorphous crystallized in a metastable phase, which is cubic, and this is not topological. So there is a particular form of GST which is topological, but which is not really relevant. Yeah.
John? Yeah. Okay, this was a very nice talk. Many things I have to understand, but I will try to on you my regular question on machine-learned potentials.
Yeah.
Your potentials are effective temperature dependent, right? And even phase dependent. Doesn't this violate thermodynamic consistency?
What do you mean is temperature dependent? So
to test them, did you develop them on configurations at different temperatures or the same temperature?
Or many different temperatures.
Yeah, then there is a problem. Your potentials are temperature dependent.
So you fit the potential energy surface. What do you mean it's temperature dependent? You fit a potential temperature.
Yeah, but the data that go in are at different potential. Well, anyway, then
you are interpolating the potential energy surface. Why it should be temperature dependent?
Did you ever test whether the heat capacity is equal to the energy fluctuation or not?
Sure.
That's no problem.
No, sure.
Okay, then my question is irrelevant. Yeah. Sorry.
The potential is fitted to configurations.
Yeah.
Okay, as long as you explore the configurations which are relevant at that particular range of temperature, you're fine. So if you want to explore new temperature, you have to add new configurations, and there are methods for adapting the data that you feed to the mutating circumstances. So in principle it is so, but that's taken into account. It's not that he does one simulation, that's it. These things are always checked. If there are things, situations which can be troublesome.
Yeah, so
and you stop it and check whether the potential is still okay.
No, it's a 2-year work of a PhD student, so the iteration of this potential by exploring different thermodynamic conditions, yeah.
Just to rephrase it, maybe saying something very trivial. Ciao, Michele. But as long as you use the same potential for all the temperatures that have been used to generate data to train it, you are okay. There is no reasons why it should not be consistent. Yeah. It may be wrong. Yeah. I mean, it may be not accurate enough, but as long as it is formally temperature independent, in spite of the fact that it has been trained, not even in spite, because of the fact that it has been trained over a wide range of temperature. So if the potential formally does not depend on temperature, which usually does not, you are okay.
Yeah. So it's a good way to interpolate. So it is not possible to extrapolate. So if you are exploring a temperature range which are too far from the training data set, probably you are in trouble. But so as soon as the data set is sufficiently large. Yeah.
Okay, during the time limit, thanks Marco again. And, now let's move to how temperature shapes the ice. Michael, Berlusconi.
Yes? Sorry.
Thank you very much for the invitation. It's a real pleasure to be here. And I've been in London for quite a long time, over 20 years, and the snow is a rare event. But when it snows in London, nothing works. And I just put this picture here because this car over here, now defunct, was my beloved Ford Fiesta, which I actually got when I was in other place where snow is not a rare event, that is Stuttgart. And in particular, I think now there's a little bit of global warming, but when I was in Stuttgart, when I arrived in 1996, the minimal temperature was something like minus 18. So it was super cold all the winter, and my then Fiat Uno didn't survive, so I got this other car. And okay, I think nobody has showed these pictures yet. This was the group when I arrived at the Max Planck Institute. You can see Michele, and this was the secretary, Frau Kack, and then you can recognize probably some of the people that are in the audience. Okay, this is me, and this is Carme Rovira, Roger, somewhere, and Jürg Gutter, and okay, there are other people joined later on that year. So how did I ended up in Stuttgart? So I was working in Cambridge at the time for the CASP competition on grain boundary sliding, and I was dreaming up a career in this location, these kind of things and so on, but I wanted to find another postdoc. And my contact actually in Michele's group was Marco Bernasconi, with whom I have collaborated when I was a master's student in the University of Milan, and he was at CISA. And so I knew that Michele was doing all sorts of more exotic things with the density functional theory. At the time, it was rigorously density functional theory. But Marco also warned me that there were already a number of Italians in the group, and so maybe it was difficult to have another one. So anyway, I sent a letter to Michele, expecting that it would not be would be considered, and then I got an answer back saying you can start on 1st of June. So someone might have put a good word for me. When I was in Stuttgart, Michele told me we can work on anything but not grain boundaries, and we end up working on something very, very different that was sugar in water, as water in itself was not complicated enough. And then I also work on nanocrystals under pressure in collaboration with Roman, and last but not least on photoactive proteins and retinal, rhodopsin, and so on. So the message I got was that actually with this simulation you can do whatever system, which has been probably a blessing and a curse in my career, because I ended up studying a lot of different things. Rather than maybe being super specialized in one, but that is, the way it's been. And again, also at the time, there were lots of different applications in the group. And then I moved back to the UK, but I was fortunate enough that Michele moved to Lugano, that is about 35 kilometers from Olgiate-Comasco, that is the place I come from. In Italy, so I always had the opportunity to go back to visit him while I was visiting my mom as well, and to keep up with all the methodological development and get in contact with people and collaborated with various people that had been in the group and so on. And the work that I'm presenting now actually stems from one of these visits and the collaboration with Matteo Salvalaglio that is then moved to London. And then also we benefited by various chats with Pablo for collective variable and so on. And that's what I'm going to present today. So again, now we're talking about snow, but really snow is made up of snowflake, snow crystals, ice that is made up by water molecules. This is what we now know, but it was not always known. But really the way that water molecules assemble to create ice crystals and then in particular very intricate and different and diverse crystal shape has still some aspects that are not completely understood. So apparently the fact that snow crystals have six-fold symmetry was known for thousands of years, but in the 17th century they started actually studying it a little bit more in details. So there is this work from Kepler, known for all his astronomy studies, that wrote a booklet somehow asking why always 6? There must be some cause for that. And at that time, obviously, molecules, atoms were not known, but there was this sort of hint that came from some studies of how to stack cannonballs, and seeing that there was some hexagonal crystal pack efficient way to stack them, that there must be some building block that would give this particular symmetry. Back in England, Robert Hooke was working with the first microscopes that you can still see in the Science Museum in London. And there's this famous book, Micrographia, that I can always find on the desk of one of my colleagues who is a microscopist and fan of Robert Hooke, who drew some of pictures of snowflakes, although they are a little bit primitive somehow. And since for any kind of study, there is also some fellow Italian that study them. There is also, again, more or less in that time, 1681, this booklet by Donato Rossetti, Canonico di Livorno, who was a professor of natural philosophy in Pisa, and then he became a mathematician at the court of the Savoia in Torino, who also wrote, again, a booklet with some a bit more precise drawing than the one of Robert Hooke on all these different shapes of the snow crystals. And then, of course, photography came. Wilson Bentley was in Vermont, spent his life, basically, perfecting the photograph of snow crystals. He had like 5,000 of them by putting a camera, combining camera and a microscope. And now there are obviously much more precise pictures, but if you look at this one, it's not very different, actually, from the picture of Rossetti on this La figura della neve, that is the figure of snow. So we know a lot of things now about water and so on. We know this is probably not even the latest phase diagram. We know that there are lots of different structures of ice, and the one that is relevant for the kind of condition that we see when, again, is known, a bit maybe lower if we are in Stuttgart, is hexagonal ice. So we can easily answer the question of Kepler, why always 6, is because the underlying lattice of our normal form of ice is actually the hexagonal one. And so the growth of snow crystal has different phases. So in a cloud, first there is a nucleation effect around the dust particle or something like that, where the crystals start growing. And then there is the first phase when the crystal is small, when that is faceting, basically. So the crystal follow the underlying lattice of hexagonal lattice, and so it becomes a small hexagonal prism. But then, as the crystal grow, the corners become unstable, and so there is an instability branching where, again, at the corners, branches start growing. And in all this happens in a cloud where there is wind and different, slightly different temperature and humidity condition, but the crystal is very small, so the conditions are basically almost the same at the 6 corners, and so depending on, the path of this crystal in the cloud, then there can be a lot of different shapes and so on. So all these diverse paths result in a very big diversity. So there is an interplay between the faceting and branching, and so faceting give the small crystals that are hexagonal prism, and then if there are other kind of condition, we can have the more complex dendrites and so on. And so this all depends on temperature and humidity. And so there is a sort of morphology diagram. This is one that is taken by a paper by Kenneth Liebrecht that has assembled a huge amount of experience on snowflakes. And he has a really nice website dedicated to it. That was the one I had at the beginning. And so the boundary of some of these temperature and so on change a little bit depending on the particular diagram, but you can see here that depending on the temperature and the humidity, basically you can have all different shapes. But we were intrigued by something here that is that at low humidity, so a low supersaturation, the crystal go as hexagonal prism, but depending on the temperature, there can be plates or prism, and then plates again. And this is quite an intriguing behavior, and we wanted to have a look to this. And okay, these are just some picture of crystals at slightly different temperature. Okay, now, if you come to King's College London in winter, this is the next building. It's not so flashy in the physics department, that is on that side. And there is a ice rink there. And as we heard yesterday from Davide Donadio, the surface of ice is very special because it has a quasi-liquid layer on the top. So we wanted to study these different surfaces and look at the different properties. So these are the various surfaces of hexagonal ice. This is the basal, the primary prism, that are the ones that are relevant for growth in vapor. This one is the secondary prism that seems more important for growth in water from liquid. And this is, okay, the cubic ice that is also, this is a metastable form of ice that we also study. And again, we are not doing anything particularly fancy for potential, but again, yesterday, Davide did a lot of mention, a lot of improvement and development there, but also that in some cases, it's still okay to use our normal classical potential. In particular, we're using TIP for P ice. And so these are actually the three surfaces of hexagonal ice. The PRIMS2, that is less interested for what we're going to do, is made up by equally spaced layers. And the other one, the basal and the prism one, are arranged by bilayers in the direction perpendicular to the surface. That are arranged a little bit different. The basal one have a sort of smaller intralayer and larger interlayer, and the opposite for the prism one. But so we wanted to quantify a little bit this quasi-liquid layer that is at the surface that pre-melts. So we can do this with a number of collective variables. Again, some developer people in the audience, as you can see from the references, in particular various flavors of the Steiner parameters that look at the neighbors arrangement, and then we have an entropy fingerprint developed by Pablo and Michele, and then environmental similarity as well, and all of these are actually implemented in plant. And they have different kind of properties. Some are good to distinguish between order and disorder, like the entropy fingerprint. Some other are good also at distinguishing different crystal phases. These are actually the local average Q3 and the local Q3. Q3 in itself not very much, and then we can mix and match and use two of them or something, whatever. We can also use a machine learning kind of algorithm for recognizing them, and this is our own that was developed by a PhD student in my group, Max Fulford, that input the Cartesian coordinate of a certain number of neighbors and then recognize whether there is water or ice, having been trained on the bulk and of bulk with, again, cut with the surfaces in such a way that it can recognize also dangling bonds. Okay, so if we measure then the quasi-liquid layer in this way, with various methods, we can see as a function of temperature, and again, these are all tip for P, ice simulation, we can see that in all cases it increases with temperature, if it eventually, diverge for the melting, but these are molecular dynamic simulations, so melting is a bit out of the thing. And then, but then we also see, and they're more or less all the same trend. This is all hexagonal ice, this is cubic ice with various methods. And there is always a little bit of difference between the behavior of the basal surface and the one of the prism one surface. Okay, and this we measure with the number of water molecule, but you can reconcile for some quantity that doesn't depend on your size of your system, like the thickness or the number of layers. And this is done with the environmental similarity. And with the tip for P water, we can see a thickness of the quasi-liquid layer in between 5 and maybe 12, 13 angstrom. So again, there's slightly difference with the various order parameters, but they all give a very consistent, very similar kind of trend. The differences are a little bit depending on the more precision and so on at the interface between the liquid and the ice. So if you want to be super precise there, maybe there is a little bit of thinking to which one to do, but again, in general, they're quite similar. Now, are there different properties for these surfaces? Well, for this liquid layer and the various surfaces, in some cases, we can actually plot also the average or the parameters, when we have it, not for the neural network, obviously, for the various temperature and so on, and we can see a little difference and some crossover with temperature depending, again, on the surface, and in particular, it's all a little bit, because there's also quite a lot of arrows, but you can see some trends. And so somehow there are some temperature regions where the basal surface seems to display a different behavior than the prism surface, and then again it crosses again there at higher temperature. Does it correlate with the different habit of the prism, of the platelet versus the needles? That is what we're trying to establish. It maybe. And so we try to do also something different to try to measure a little bit more, again, within all the limitation of the methodology, the kinetic of growth. So in the quasi-liquid layer, there are two interfaces, the one with the vapor and the quasi-liquid layer, and then the one with the ice. And they are both important. But then we're working at low supersaturation. So we assume basically that that when the water molecule arrive, they are quickly introduced, they quickly become part of the quasi-liquid layer, and so that the limiting growth time scale that is important in this regime is the one associated with the incorporation of the quasi-liquid molecule into the crystal lattice. And so to sort of implement this assumption, what we did was that we we basically pre-melt a part of this at the supercool, and then supercool it at the temperature that we were interested in, and then study the rate of crystallization of this part in the bulk. And it's not, I mean, there have been various studies in doing something similar in the bulk. This is a little bit different because, again, there is the surface that limit what can crystallize. Okay, so these are basically the kind of simulation we did, and we did multiple replicas and various temperature and so on, and some fitting procedures, linear piecewise fitting procedure that would somehow automatically find the change. And then with this we can estimate a rate of growth. And again, we can see some crossover, again, with a little bit of cautious because there are obviously statistical errors and so on, but for some part, the prism always goes more quickly than the basal, but then there are some small interval in the temperature that is where the opposite happens. And so somehow, and this one somehow correlates in the case of tip for PIs with this crossover between platelets, needles, and platelets that is seen in experiments. Now, if we do the same thing with the coarse grain potential, like the MW potential, that is basically stealing Weber potential a bit modified for water, the results are a little bit different. But it's a great potential to do lots of tests and work with the students to do things. And so the quasi-liquid layer is much smaller, so it's much more icy. There are no direct explicit hydrogen bonds, so it's much more icy. There are no crossover in the quasi-liquid layer thickness, and the prism is always going faster than the basal, so this would predict only platelets. Obviously, real, so we're done T for PI, so we're done MW. It's a bit different than the real stuff, but again, T for PIs correlates better with the experiments. And you can see here also something that, again, was mentioned before by Marco, in the sense that there are different driving force for crystallization. There is the difference between the free energy of the liquid and the solid, but there is also diffusion. So in principle, one could expect that at very low temperature, the crystal will crystallize very fast, but actually this is offset by the fact that the molecule diffuse very slowly. And so we have actually two different driving forces, and so there's a maximum that in the case of T for PIs is about 260, and in the case of MW is lower temperature, 240. And okay, this is an attempt to compare also with some experiments, but again, there is some, these are our results, and then these are different, the experiments are always in different parts. And some that are done in thin films that are reasonably comparable. There are some other here that do not compare, but basically this is where we are, and then we did, I don't know how much time I have, 4 minutes, perfect. So we've done also some analysis, in particular of the, so you can see, well, oh, you could see here before, we did analysis, let me see if I can go back and redo the movie, of the the 4 bilayers that crystallize before arriving to the quasi-liquid layer in equilibrium, and these are some estimation of the roughness of these bilayers for the basal and the prism at 2 different temperatures where, again, there is an exchange of growth rate. And then, okay, we can do also some analysis of the mechanism, and at 260 K, as was mentioned before, the basal goes more through a crystallization, although yesterday for the melting, but it's basically the same. The basal goes more from a bilayer by bilayer mechanism of crystallization, and the prism a bit more of a 3-dimensional collected molecule mechanism. So we're not the only people that ever look at these things. So what we did that was different was to try to measure directly this rate of crystallization. There have been other work. One was from Davide that he already mentioned yesterday, where in particular they look at the transitions, and another one is from the group of Louis McDowell, where they look at the properties of the surfaces and the phase transition of the disorder and roughness of the surfaces, and in particular, again, Davide was looking at the effect of the presence of ion, sodium and chloride, and so on. And again, our work is and they predicted also this kind of phase transitions of differences in the habit of the crystals, looking from a different perspective. So what we did was is a complementary kind of work, trying to quantify the rate directly. Okay, so this is basically the conclusion. We quantified this algo rate and correlated it with this different shape of growth with temperature. And last but not least, the acknowledgement. The work that I presented today has been mostly done by Jiong Shi, was a postdoc, a PhD student in my group, and is now doing a postdoc in Canada, and Maxwell Fulford, that was another PhD student in my group that now works at Deutsche Bank, and then with the support of some master students, and Matteo Salvalaglio, and I should also acknowledge insights into various collective variables by Pablo, and great thanks to Michele for all the inspiration and so on. And we have done also a lot of metadynamic simulation that they still have to be a bit rationalized, so we didn't manage to get them in the special issue, but we have another paper, again, on a different topic that is ion channel, that is just going to appear soon. And thank you very much for your attention.
Thank you very much. Questions?
So thanks, Carla. I had a comment and a question. So many of the water models, including DFT, have a challenge of characterizing the orientation of water at the interfaces. So Michel Bon and his group have done experiments where they do SFG to probe the water. Have you looked at how well tip-4P ice does for this?
Not directly. We did some work about orientation of molecules and things like that. We did a little bit of analysis, but not a super detailed analysis of that.
I mean, orientational polarization is very hard to get right, even with machine learning,
Yes,
stuff.
yes.
Okay, thank you for the talk. I really enjoyed the topic. You do find the crossovers in the growth rates, but I didn't understand if that is in good agreement with experiment or not. And the second thing that I have in mind is that I guess in the atmosphere this happens is growth from the gas phase, and I think you're measuring from the liquid. Could you comment on these two things? Thank you.
The agreement is actually good. In the sense that so so it's very small kind of interval where there are these different things. So it has to be taken with a pinch of salt in a way. But the crossover is somehow in the right space. Now, there are errors, okay? So you might believe it or not. I mean,
There are challenging simulations, not to get.
Yes, there are some simulation, there are some multiple replicas and so on, but there are still errors about that. So in this case, more or less, there is a crossover. If you look at the crossover that we look with the properties, if you want, of the quasi-liquid layer, they are a little bit different in the sense there's still something very close to the melting temperature, but again, this is the thing. The other questions.
No, very short, because it was pretty much the same idea as Pablo's question. When you're simulating growth of a snowflake at very high humidity, right? So
no, low humidity.
Well, no, because you have an interface liquid water. In low humidity, you would have basically a dry, let's say, a dry ice surface that is absorbing water from the gas phase. It's somewhat complementary to what we did, because we are looking at the roughness of the system at equilibrium. So we say how can it accommodate water from the gas phase. You're looking at crystal growth from a two-phase simulation, basically. So it's, in my opinion, you're simulating some sort of high humidity.
Short answer, okay.
Okay, so this is our basically argument that the thing that for low humidity is important is not just the time scale of the absorption of the molecules on the surface, but the other one. So this is our argument.
Okay, okay. Now I think it's coffee time. We thanks the previous three speakers again, and we come to on time. Oh, just here, okay? Just inside.
I didn't see the argument, so it was based on the fact that the limiting step is the incorporation of the molecule to the lattice and not of the gas molecule to the
see,
surface.
this is basically what.
No, it's a good argument. I just didn't catch it. It's a good argument. I was thinking, you know that there is this new coarse grain potential called ML4. So it's similar to what? It's similar to MW, same cost, but it has been fitted to both experimental properties and data of the T4 2005. And as a result of that, it captures the thermodynamics incredibly well. I think so. Some things where MW fails catastrophically, this other one gets it right. So when I was in your plot of MW failing, I was thinking, well, maybe this other potential does work well. And also, I guess moving forward, now that it's becoming increasingly common to see models based in couple cluster, those ones are almost drinkable water. Well, it's a lot of work not to do these things. Yes. The results are really good.
sono contento che vedi il by layer, perché il paesani tutte le volte mi rompe i coglioni. Ma ci credi veramente? Sì, cioè questo sì, all'interno. Io sono l'influencer.
Stavo parlando della loro high specialization. Non so se ti ho convinto, però...
No, ho capito, I understand your all of your somewhat. No, of course, you want to pick your points. But it's a great work because it's somewhat complementary to what Luis and I do, because we were systems and equilibrium characterizing darkness. Slightly disagree on some, but it's more like the position of the an hour's perspective. So for the roughness thing, for some reasons, the 2005 is, of course, everything is shifted, but it does a better job, and I think that Carlos Vega and his group have an argument about the parameterization overall being better for 2005 than 2005, which is skewed towards getting closer. Also, they have a discussion about whether the so 274 to 72%. I don't know why they never tried. Well, I don't know. Once in a while they change idea because you change method, and I think the best method to do these things is to phase. A large, huge system to phase. They find, yeah. Okay. Because they were changing every once in a while. He was changing the reference. He was moving high and low. Yeah, it depends on the paper. No, I'm not saying effort. I think they were refining it and finding slight errors. I don't understand. I think they're getting better. They were not changing the
No, it's not a paper in Carlos, a paper with
don't see the G, it's like yeah. Come.
Where you from? You're
From Italy.
from Italy. Come on, this Italy have this name. Can you show it?
Yeah, let me see if I have. Oh no, I messed up my. Of course. Salvalaio.
Savalayo.
Salvalaio.
Italy, where from?
I'm from close to Milan.
Close Milan.
So I crashed my keynote. Let's see.
IT.
Sì, ho connesso e stavo cercando di controllare che la mia roba fosse a posto.
Ok,
Ma
funzionato?
ha funzionato, adesso magari lo what do you mean? Ah, yeah, shall I put it up? Okay, I will. This is off. Matteo. Yeah, Salvaglio. Yeah, that's good. That's good enough. Okay. Microfono. Ok.
Test.
Sì.
is any still some people outside? Okay, please have your seat. Okay, let's move to the second part of the morning session. The speaker is Matteo Salvaggio. I'm sorry. He's talking about the molecular crystals without sampling phase transition. Please, yeah.
Okay, thank you so much for the introduction and for the opportunity to speak here. I'll jump right into the topic. And since this morning Daniela outed me as an engineer, I thought I had an engineering slide. And the engineering slide is about why should we care about predicting molecular crystal polymorphism. And of course we care because it's fun, it's hard, and it's an interesting problem, and it involves a lot of rare events and interesting things that this community cares about. But it's also important because it's practically relevant. So recently I've been involved in kind of sketching out a potential pathway between developing a chemical process, a conceptual process design starting from molecular structure for crystallization. And in this process, the details are not important, but the important thing is that there's a lot of computational chemistry that goes on, and understanding what crystal form actually precipitates when you have a given organic molecule plays a central role in this pathway. In other words, if we don't know what is the solid phase that will most likely precipitate when you have a given molecule, we cannot really predict how this molecule will crystallize, and therefore we cannot design a process. And if we want to push for having an in silico design pipeline, it's essential that we solve this problem. So this very practical application is actually intertwined with very, very deep theoretical questions that relate to how polymorphs are selected, how the selection depends on thermodynamics, in kinetics, and so on. So the field that deals with predicting what crystal structure will emerge from a given process, it takes the name of crystal structure prediction, and it goes a little bit like this. So you have a molecule, and this molecule can assemble in multiple ways. Many of you have seen this slide to death. This molecule is a molecule of ibuprofen. It's very familiar to any of us. For those in the UK, it's very familiar. And basically, ibuprofen is the same molecule, but can assemble in many different crystal structures, a little bit like Lego bricks that can assemble in different forms. And the typical result in a crystal structure prediction study is this type of diagram where you plot all the possible crystal structures as a function of a descriptor, usually the density of the crystal structure and of their energy. And in this description, energy is used as a proxy for probability of observing the crystal structure in a given system. So the lower the energy, the most likely the crystal will be to be observed. Essentially, it's a proxy for the thermodynamic stability of the crystal. Now, there is a problem because I color-coded the 3 observed polymorphs in this landscape, and you can see that experimentally we know 3 forms of ibuprofen, but there are many more local minima of the potential energy that could be stable structures of ibuprofen. So one of the questions is, okay, once we have this big landscape, what should we do to understand which one of these local minima actually pop out and can be observed in an experiment? So the question is, which crystal structures can actually be obtained and how can they be obtained? And we worked a bit on this problem, and we boiled it down to a few questions that can be tackled with molecular simulations and the methods that are developed, for example, by this community. And the first set of questions is, which one of these crystal structures can actually survive at finite temperature, and what is the relative stability at finite temperature? So not just what is the relative energy, but also the relative free energy with all the anharmonicity that comes with these complex molecules. And then, if we know which structures can satisfy these conditions, we can start thinking and asking ourselves more interesting questions that are related to kinetics. This type of process kind of defines also a funnel. So we start with many crystal structures here at the beginning, and then as we progress towards more refined questions, we get less and less structures. So a little bit of work that we did to start tackling this question essentially was starting from a crystal energy landscape, a little bit like the plot of ibuprofen that I showed you earlier, and using molecular dynamics and metadynamics to identify two kinds of local minima. This is a familiar example. This is urea that we worked on to death in the Lugano days. And of course, this was my first test system. And it turns out that Sally Price at UCL had already a very nice crystal energy landscape of urea. So we started using MD and metadynamics to understand the two things. One was essentially which one of these structures are labile. So they are embedded in a local minimum that is so shallow that as soon as you turn on the temperature, essentially they melt and they're not relevant. And which one of these structures actually, so this is an example of a labile structure that loses completely orientational order as soon as you turn on the temperature. And the second step is which one of these structures are prone to undergo solid-solid phase transitions. So they are in a local minimum that is shallow but is adjacent in configuration space to a different crystal structure. So they transition to that crystal structure, and maybe at finite temperature they might not be even distinguishable between the two. So this is an example, again, of urea that urea is really friendly. Sometimes it does these things also in unbiased MD, so you can see these type of transitions. So this process was somewhat successful in the sense that we were able to reduce a very large set of 0 Kelvin static structures, here represented by these points around the circle, into a smaller set of relevant persistent structures, at least within the approximations of the potential that we use for these things. Now, the question that remains is what is their stability at finite temperatures? Once one has this set of reduced structures, the question is, okay, how can we efficiently compute the relative stability, retaining essentially without undergoing the usual harmonic approximation approach? And the immediate approach to this would be to use metadynamics. Use metadynamics to explore phase transitions and map out a free energy landscape function of order parameters that are able to distinguish those crystal structures. And here it's an early example of this attempt done on CO2. In this case, of course, we have two order parameters. The two order parameters can distinguish two local minima that are corresponding to two metastable phases of CO2 under pressure. And with metadynamics, we can discover additional states, for example, defected structures. But most importantly, we can integrate out and compute a delta G as a function of, in this case, of pressure. So we can investigate the relative stability and so on. So in a way, we do answer that question. What is the most probable structure at a given pressure and temperature? Now, the problem, this would not be avoiding rare events. This would be like taking the rare events face on. The problem here is that it is scale. I mean, when we look at the typical CSP study, you have hundreds of structures. Even when you go through a successful reduction using the protocol that I tried to sketch, you can reduce quite a bit, but not really by an order of magnitude. Here, this is a real result on ibuprofen, where we start from 550 crystal structures, and then after jiggling and wiggling, we get around 200, which is a great result for Sally, for example, but if you want to run an harmonic free energy calculations on 200 structures, you're still out of luck. So at this point comes the core of this idea and this, let's say, this integration of sampling and machine learning that we have starting to implement in this workflow. And Edgar Olenovics is the PhD student that's behind all this. And essentially, at the end of this pipeline, we have a set of metastable states that have been locally sampled ergodically. So we have MD data related to the equilibrium configurations of those metastable states. So it's something like this. We have a high-dimensional free energy surface. We have sampled the local minima. We have never seen any transition. So we have never seen any rare event between those basins. And what we want is a method that allows us to efficiently compute the difference in free energy between configurational ensembles of any I and J of these methods that have distributions that do not overlap. So the answer that we try to attack to obtain these differences in free energies is essentially targeted free energy calculations or targeted free energy perturbation that are enabled by machine learning. So to understand a little bit the context to where we want to integrate machine learning and this type of calculations, I put together a bit of a recap on the method. And the idea is that, okay, if we start from free energy perturbation, usually we have a distribution, let's call it P of x, where x are the configurational coordinates, and A represents the state, could be a polymorph, for example. And this is the distribution that we would like to sample, for example, the one we sample from MD. And usually when we do free energy perturbation, okay, these are the usual definition for this distribution. Z is the partition function, F is the free energy in reduced units. So U would be any dimensional potential energy. Now, usually when we do free energy perturbation, we have a different distribution, let's call it Q of x, that is not the distribution we would like to sample, but it's an easy distribution that we can sample. And then going through some math and some algebraic passages, we can obtain the usual equation for free energy perturbation. But the important point, and the reason why I put it on the screen, is that we can cast it with this phi of x, which is a generalized work function that is the core of the targeted free energy perturbation that I'm going to talk about in a moment. So this is not fancy or new, it's just a free energy perturbation equation. And the point of this is that to use the free energy perturbation equation, you need overlap between the two ensembles. So if the easy distribution to sample doesn't overlap significantly to the distribution that we would like to sample, we are in trouble. And targeted free energy perturbation attacks this problem in a different way by building essentially a map. Essentially, by introducing a mapping between the coordinate x and a different set of coordinates y function of x, we can actually define, I mean, if this map is differentiable, we can compute the absolute value of the determinant of the Jacobian of this transformation. And if we know that, we have a definition for the distribution, let's call it Q, in the space of these new coordinates x. And the result that we are taking advantage of is this expression that comes from a fantastic paper from Jarzynski of 2003, where essentially he generalizes this work function to include the mapping. And the cool thing now is that we can sample this space Y, and then if we know the mapping, we can transform back and obtain an estimate of f of A that we are not directly sampling. This is cool because this type of relationship doesn't require any overlap, and it's exactly the type of method that we would need if we have a bunch of data that is scattered around where you don't have any transitions and that has been generated locally. So, of course, the problem becomes getting the map. And before that, this also gives us a route to compute differences in free energy, if we have different states that we map to the same reference space. So in this case, imagine you have two polymorphs, A and B. They have their own distribution, but we map them to the same reference space. We can compute, essentially we can realize a thermodynamic cycle and compute a free energy difference between A and B without actually sampling any intermediate state. Of course, this requires to have maps. In particular, here to have maps that map from A and B to the same space described by these coordinates y, and to the same distribution Q of y. Now, this is easier said than done because, again, mapping becomes a problem. Let's say if we are mapping this red state onto the blue state, it's easy because the map is just a linear scaling. We're just shifting and stretching a distribution. One can easily guess what the transformation should be. But of course, first of all, we live in high dimensions. These problems are very high dimensional, and they're also very much nonlinear. So even in one dimension, if you have a multimodal nonlinear distribution, the map is non-trivial. So the problem becomes finding the map, and this is where we were forced to start studying a little bit of these methods, because this is where it becomes important to essentially widen the horizons and start using these type of processes, these type of methods. So here we turn to flow-based generative models or probabilistic generative models. And the idea is that we can essentially represent that map as, let's say, if we look at it in general terms, as a bijector that is a function of a representation of the coordinates. The coordinates are indicated here as r of I, and a set of parameters, theta of I. And the architecture of this bijector is typically built on multiple low-dimensional coupled bijectors, for example, multi-layer perceptrons, and a convenient P0, so a convenient reference distribution that we use is a uniform distribution, because it's typically inexpensive and generalizable. So if we have this in place, let's say we have this scheme of bijector, function of representation, and so on, we have an expression that gives us this qi function of the coordinates and the parameters if we know P0. P0 is analytical, so if we know the map, essentially we can compute this distribution. And by training, essentially training by example, following one of the recipes in the Boltzmann generators paper that came out in 2018, we can actually obtain a Q of I that approximates very closely the physical distribution that we are starting from. So in practice, we start from something like this, and after training, we get to something like this. That's a very familiar looking free energy surface in 2 dimensions. And the idea is that these bijectors learn how to transform this P0 distribution to the actual distribution of the system we have sampled. Okay, so having the map is important. The second important ingredient to be able to use this type of methods for ranking polymorphs is the free energy estimator that one uses. And in that case, we turn to alanine dipeptide because why not? And we generated a data set of 4 states that are arbitrarily, essentially, mapped onto the configurational landscape of alanine dipeptide. And the characteristics of this data set is that there are no transitions between any pair of these states. So all the configurations come from each one of the states. And then we run this process, and as you can see, these are the potential energy distributions for states 1, 2, 3, and 4, and the color represents the training batches. So going blue to red, we go from untrained to trained, and what the maps are doing is essentially transforming the distributions of coordinates that were completely random at the beginning to coordinates that are qualitatively indistinguishable from the alanine dipeptide ones in every one of the states. Now, you can see that the final red potential energy distribution overlaps very nicely with the black reference, but it's not perfect. And this imperfection is due to the fact, it's due to the fact that the training of these maps has a finite accuracy. It cannot match exactly the Boltzmann distribution, and a consequence, for many users this is more than enough, but if you want to get free energies with a very high accuracy, it's not enough. So one has to resort to reweighing. And here we have examined a little bit what type of reweighing we should be using. So if we just do averages, this is the difference in entropy of the different states. And you can see that there are some systematic errors that are due to the inaccuracies of the maps. But then if we do, this is one-directional Zwanzig-like reweighing, it's better. And then if we do bar on validation data, it's actually very good. And if we do M-bar, it's even better. So the message here is that if we use multi-directional or bidirectional reweighing techniques that essentially converge free energy differences in a self-consistent manner, it's the approach necessary to achieve a very accurate estimate of free energy differences with this type of methods. Okay. Of course, alanine dipeptide is not a crystal, so the next thing to do was, okay, let's try to see whether we can export this type of approach to crystal lattices. So we looked at 2 ice polymorphs, and we asked ourselves whether the representation matters. And here we are comparing, essentially, what we are doing is training maps that go from this type of distributions to these distributions, where essentially if you plot the marginal on, for example, a dimension of a box axis. Here, the two MD data and model are present, but essentially they're indistinguishable. And the question here came together because if we change the representation, I believe this is another example where we have a much bigger cell, and this works, again, at different temperatures. But the point here is that if we change the representation, the same data can be used less or more efficiently to achieve this goal. And so we tried to use a Cartesian representation in this type of scheme. And the Cartesian representation, this is a difference in entropy between the two different polymorphs for different system sizes. So blue is 16 molecules, 32 molecules, 64 molecules. And in black, it's a reference that is computed with the Einstein crystal method. So state-of-the-art free energy perturbation reference method. And the idea is, okay, we can use a naive Cartesian representation. At low temperature, we can do well because fluctuations are small and the system is very much harmonic. But when we go to high temperatures, we can see that we can still get something that is qualitatively correct, but the uncertainty is so big that for our purposes of ranking thousands or hundreds of structures is not really feasible. And you can see that if one tries to essentially extrapolate to the infinite size limit the difference in free energy between lattices, in the case of low temperatures, you can get away with this type of errors, but for high temperatures, it becomes completely unusable. If we use the same data, but we inject some physics intuition into the representation, so in this case, instead of using Cartesian coordinates, we use a relative orientation and position. So essentially, the exact same data can be used a lot more efficiently. Now, the low temperature limit is essentially exact. I mean, the errors are very small, smaller than Einstein crystal, and the high temperature is usable. So the message here was like, okay, besides learning how to do these things with lattices, we also understood that injecting physical knowledge into the representation is part of the game. And this was key to do the final step and develop an architecture that could do this for molecular crystals. And here, so the architecture is complex, and Edgar is the architect here, but the message is that essentially what Edgar has done has been decoupling the position of a Cartesian block of 3 atoms that is treated as the ice, as the water molecules in ice, and then to the flow of the configurational degrees of freedom that define what the conformer is. And then there is a complicated scheme that couples the two flows, and it couples the two flows in such a way that one of these models can actually learn how to transform a distribution that is different for every polymorph into a reference distribution. Okay, does it actually work? Sorry, I have to say that this complicated architecture is described in a somewhat outdated preprint. This is due for an update soon, but the basics are there. And does it work? So we tested it on a system that we worked on already in the past, which is succinic acid. Succinic acid is a deceptively simple molecule because it's small, very small number of atoms, but many rotatable dihedral angles. So one needs to be able to take into account these conformational degrees of freedom properly. And succinic acid has 3 polymorphs, and 2 of them are just packing polymorphs. So there is the same conformer in different arrangements, but one of them is a conformational polymorph, where the molecule is in a different conformational state. It's this state gamma here. And what I'm showing here are the absolute, so with respect to the reference state, free energies, lattice free energies in KTs, where again, color is the result from the probabilistic generative maps, and ECM is Einstein crystal results. And so the results are essentially indistinguishable. This is also true for the lattice entropy. And a good news for us is that the difference in free energies are relatively insensitive to the two-system size. So if we take the difference in free energy, again in KTs, we can see that it's relatively insensitive to how large our supercells are. Of course, succinic acid is nowhere close to a pharmaceutical molecule, so the next step was to look at a small pharmaceutical API. So this work is partly funded by a pharma company, and when they look at this, they don't really see a pharmaceutical, they actually see a toy model, but it's a lot more complex than succinic acid, and the short message is that it works, and the results, though, are extremely sensitive to what force field you use. In this case, GAF, for example, of the shelf gives us the incorrect ranking of the polymorphs, while OPLS works well, but the reality is that we need to step up our game here. And that's kind of the point of the, I'll get to it again at the end. And then I just flashed this result where essentially we can go to a reasonably large API, and here we're pushing the limit of what the representations that we're using can do, and it also works. But there are some polymorphs that are more anharmonic than others, and for which, for large cells, the uncertainty becomes borderline usable for those strict ranking purposes. Okay, so I just flashed one other thing, which is that I don't tell you how we do it, but we can do it also as a function of temperature and predict crossing temperatures, because it's that are an important experimental observable for this type of problems, and we are collaborating with a community that measures this type of things to essentially compare these methods with state-of-the-art. Okay, so this takes me to my conclusions. There are a few considerations. So first of all, this can be done, but it's important to remember that free energy estimators are key, and the low variance ones, bar and bar, should be preferred. The representation is key, and the number of force field evaluations compared to reference methods, for example, Einstein crystal, is substantially reduced. However, the computational costs associated with training the maps must be considered, of course. Normalizing flows that Pratyush showed us are limited by the number of degrees of freedom that they can handle. And I don't know where our creativity in developing these coupling schemes will run out, and we will not be able to do it. But the hope is that that limit will be sufficiently large that we can do interesting systems. And an important point is that the training cost is almost invariant with respect to the level of theory that one uses to generate configurations. And this opens up the possibility of doing these things at a level of theory that is much larger than the classical potentials that we've been using to test these ideas. Okay, this takes me to another example of when instead you sample a transition state. So I have my anecdote. I have to do it. Okay. So as Daniela said, I'm an engineer, and I feel very privileged that I was given a chance of doing this stuff in your group, Michele, in Lugano. But together with computation, I also had the task of driving, and it happened multiple times, but one was memorable, and we know that every time you have a rugged free energy landscape between two states, so that was Villa Garbald, this was the lab, and this was the minimum free energy path. But sometimes fluctuations take you far away, right? So we ended up doing a different path, and this path, while the other one is quasi-diffusive, this one is not, and it has a transition state, which is the Splugen path, which I checked is 2,100 meters high. And I have a snapshot of a group picture in this transition state that also shows some of the people here. So the faces, the green faces in this photo are totally my responsibility because I was driving the van. And you can see our chair, Ali, Claudio, Enrico, Gibo, that for me was, Federico Giberti, that for me was instrumental to feel part of the group, and of course, you, Michele. So I thank you for your attention and for the opportunity, and I'm open to take any questions.
Thank you very much, Todd. Questions, comments? Questions, comments?
Thanks, Matteo. It was fun and enjoyable. Now, one of the first examples that you showed was ICE 11, proton disorder. So the Einstein molecule, or the Frenkel-Ladd method, does not get...
And our doesn't too. We are comparing to the non-proton disorder. So the aim here was just to check that our results were giving us exactly what the Einstein crystal method was giving us, and we were using the analytical correction for, we would be, in case of a real application, we would be using the analytical correction for proton disorder.
Maybe in the future?
Exactly. No, but it seems like a little thing, but to actually tackle proton disorder, one needs this model to be invariant to permutations, which is non-trivial, and yeah, we're thinking about it because it will be also important for liquids, but it's not easy, and I'm not sure I'm competent so I need to study more.
Okay, the future and always more things to do.
Yeah.
Congratulations on the work.
Okay, thanks, Matteo. Really, really nice talks. I have two questions. The first one is, so you have really pushed normalizing flows to lots of atoms, but I'm sure you have also considered doing it in solvated systems.
Yeah.
What's your thought on that?
No, it's similar to Pablo's. I think to do it in solvated system, you need to have this invariance, and it's non-trivial, and I'm not sure we can do it with this scheme.
Could you do like Bloom-type degrees of freedom, hydration states, and things like that?
I don't know. The reality is that I don't know.
Okay, and the second question, probably you won't answer it, but you showed that slide with the temperature transition. Are you running simulations at all temperature, or is there some extrapolation going on?
Yes, I can show you. I can show you, because I knew that this question was coming. So what we are doing here is that we are taking essentially we are doing this business of training the map for a reference temperature. Then we do it for a fixed cell. The fixed cell is the average cell at the correct temperature we want. Then we promote the free energy computed this way to Gibbs. And then we run landmarks every, I don't know, 50K here. And then we do MBAR.
Okay.
And we found that this is a lot more efficient than training a map for every temperature, and more efficient than training, because we also have a version of these maps that can do more polymorphs, but it's also more efficient than doing that. So in terms of number of force evaluations, energy evaluations, so in terms of computational cost to go higher level, this is more convenient. And the thing is, I'm not sure I can say, but this estimate of the transition temperature for that force field is really good and competitive to other.
So if I get it correct, your MBAR is extrapolative in the value of the free energy, but you're not generating samples at these other temperatures.
No. We are generating samples at all the temperatures that I'm listing here, and we are interpolating with MBAR at the unseen temperatures.
Yeah, so at the unseen temperatures, you don't have samples.
Yeah.
Okay. I would like to close this talk in 10 minutes. Thank you again.
Thank you.
No? How to pronounce it? Is here something?
Can you hear me? Hello?
No?
Yes? No?
Yes.
No, I think so, yes. Give me a second to put on the video here. Very well, so thank you very much for this opportunity. I'm thrilled actually to present part of my work in this momentous occasion. And so thank you, the organizer, and all of you. And I want to shift gear, unfortunately for you maybe, and so I will talk about, not about StatMech. Actually, I have some StatMech at the very end, but I will talk about redox properties of iron-sulfur clusters in redox proteins. And these clusters are maybe the most ancient cofactors in proteins, and there are many proposals where it is postulated that the origin of life is due to them. So the first form of life developed on sulfur-rich environments and iron-rich environments, and so the first form of life incorporated these elements for respiration and so electron transfer and so on. Iron and sulfur forms a variety of cofactors, and so you go from very simple structures containing just one iron with some ligands, and you grow in complexity. As you can see, you can have 2 irons, you can form cubes, and more complex massive structures like here. And they have a variety of functions. I mentioned electron transfer, of course, for respiration, and but they also have catalytic functions, and they catalyze some of the most remarkable reactions in nature. For instance, nitrogen reduction to ammonia, and this is, I lost the pointer. Oh, where is it? So it is the top right cofactor here that is responsible for the nitrogen fixation in the environment. This is an oversimplification of the class of the iron-sulfur clusters that we can have. There are other forms, but for simplicity, this highlights very nicely the degree of complexity. So today I will focus on the cube there. It's called cubane. It contains 4 irons and 4 sulfurs. The irons are at the vertex of a tetrahedron, the same for the sulfurs, and these 2 tetrahedra compenetrate and they form that distort cube there. And this is the most ubiquitous and versatile motif that we can find in nature. So why I'm saying that? Here I just show the range of redox potential. So redox potential, just to remind you, is the propensity for a species to accept or to donate an electron. And here I report the range of redox potentials for 3 simple cases. The rubidroxine-like complexes, just 1 iron. They span a very small potential range. Then there are the 2 iron clusters here that they span. It seems that they span a very large range of potentials, but these 2 classes are very different. They change ligands, and so you cannot really compare the 2. What is more remarkable are these cubes, even having, for instance, only cysteines as ligands. So the cysteines, as you can see on the top figure, are ligated to the iron atoms. They span a range of potential of over 1 volt, which is truly remarkable. And so the question that I ask myself is why the same motif spans this such large redox potential range. And of course, the next question would be, how do the structure and the environment where these clusters are encapsulated tune this versatility? So in this talk, I will try to answer 3 specific questions. The first one is how electrostatics of the protein environment and structural distortions of this cluster imposed by the protein scaffold itself modulate the redox potentials. And I will do this with a very simple model. And then I will try to generalize this model looking at the available crystal structures of proteins containing these sort of clusters here. And then going to a more detailed level of understanding, I want to see how the dynamics of the protein modulate finally the redox properties. And I will do this using the iron-iron hydrogenase as an example. So before moving on, since I usually run very late, but I hope it will not be the case today since there is lunch after my talk, I want to acknowledge the people involved in these studies, my group on the left, and in particular Bushra Dereli and Bruno Jacob and Marcel Bayer and Bojana Ginoska, and also Kushbu, who contributed to this study, and 2 of my collaborators, Sotiri Santeas and PNNL, who help benchmarking DFT against post-hoc trifocal calculations, and John Peters, who measure redox potentials for us for a variety of proteins, and we are collaborating with him to study the iron-iron hydrogenase also. Very well. So before delving into the three questions that I will outline, I want to spend a few words about DFT and redox potential. So we calculate redox potentials with DFT. We cannot do otherwise. And the question is, of course, how good is DFT for this kind of properties? So here is a paradox, because it is very well known that DFT fails miserably to reproduce the energetics of spin states. It doesn't reproduce the correct spin ladder, and so you cannot study excited states with DFT. And, but yet, in many cases, DFT produces results for the redox potentials which are reasonably good. In this case, for this diiron cluster here, they are better than, compared to experiment, than highly correlated electronic structure methods. And so, of course, DFT predicts well these properties for the wrong reason, of course, there is some sort of error cancellation, and this is very useful, but also very risky. And so you cannot just assume that you are doing well, and each time you have to benchmark your DFT flavor against more accurate calculations, I would say. So now, I want to start from analyzing the role of geometric distortions. So if you distort this cube, how you change the redox potential. So you can do this in a very simple manner, truly simple. And so any distortion in the harmonic approximation can be described as a superposition of harmonic normal modes. And you can quantify also the level of distortion, so the magnitude of the displacement along a given normal mode, just using, for instance, an estimate of the displacement at a given temperature based on the square mean displacement for an harmonic oscillator report there. And in what follows, in the next few slides, I will use actually the vertical electron affinity for a number of reasons as a proxy to the redox potential. So here is what we get. So this is the effect of on the redox potential, and so the change in redox potential from an equilibrium position as you displace the atomic coordinates along a given normal mode. You can see that there are modes that influence the potential more than others, and so you can assume that distortions along given symmetry directions are more effective than others. In particular, you can see that modes with symmetry A1 and symmetry B2 have the largest effect. And interesting that all the distortions that are invariant with respect to the C2V subgroup of the space group of the cluster, which is a D2D, actually have the most significant effect. And that is easily explained in terms of electronic structure. Those are the kind of distortions that alter the energetics of the LUMO the most. Here is an example, for instance, for the top mode. What you have is that if you have a displacement along this normal mode, here this corresponds to an elongation of the cube along the principal axis to C2, and that is the typical distortion that you observe actually in proteins. You can have an elongation or a compression along that axis, and that is the effect that you can see in the redox potential. So just looking at the sigma, a displacement of a sigma along the normal mode, you have a change of even 0.1 volts, and the displacement that you have in terms of atomic coordinates is minimal, just 0.1 angstrom. So it is truly nothing. So you can say that yes, distortion play an important role. Yes, but of course, as you can immediately understand or foreseen, that electrostatics plays even a larger role. And so we probe the effect of electrostatic with a very simple model. Basically, we build the van der Waals surface around this model cluster here. And we roll a charge probe around the surface. And actually, it is not, we didn't use a van der Waals surface, but twice the van der Waals surface to mimic close contacts like hydrogen bonding. We tested different charges, but if you have only one charge, the response is linear, and so one would suffice. So the results is somehow interesting because there is a large positional dependence on the redox potential of the charge. So here I'm representing the value of the change in redox potential for placing a charge at different positions. So if you have a charge in the red region, it means that we make the cluster harder to reduce. If you go to the blue regions, we make the cluster easier to reduce. And actually, you can see the movie is too bright on the screen. But you can see clearly that there is this blue region where you have a large shift toward more positive value, which cuts the face of the cubes. So this positional dependence actually decreases very quickly with distance. So you can see it clearly in this figure here. If you are in close contact, twice the van der Waals surface of the complex, you can see that you span a very large range of potentials, also almost 1 volt. But as you go to larger distances, basically as you are beyond 15 angstrom, you don't have any positional dependence anymore. Of course, you have a change in the potential because you have a charge somewhere, right? And so you shift it from the value that you would have in absence of a charge, but it doesn't matter where you locate it. And so you can assume that in a protein actually is not the total charge of the protein that makes a crucial effect in tuning the redox potential, but the charges nearby. And we wanted to explore actually this, looking at the actual crystallographic structure of proteins containing iron-sulfur clusters. So we wanted to understand if there are actually distinct underlying electrostatic motifs between different classes of enzymes. Here I'm reporting various cases of proteins containing iron-sulfur cluster. You see you have tiny proteins like ferrodoxins, which contains 2 cubes. You have much larger constructs, which contains chains of cubes that serve as the proton relay. Protons jump from a cube to another, and that is how the transport of the electrons works. And you can see that the electrostatic pattern of these different proteins is rather different, right? But there are commonalities. So we look at all the proteins in the PDB that contains iron-sulfur clusters. We found more than 2,300 proteins containing iron-sulfur clusters ligated to 4 cysteines. And among these, there are more than 800 unique clusters, and so no redundant. And by this, I mean that we exclude also all the mutants of a given protein. We exclude the same structure but solved by different groups, and so on. And we evaluated the electrostatic potential around the cluster using a simple computational approach. We use charges from amber, and for clusters and data cofactors in-house force fields. And we calculate the electrostatic with this adaptive Poisson-Boltzmann solver in a continuum solvation model. So we cluster all these images together, and if you are interested, I will tell you later how we did the clustering. But as you can see here, this is a projection of the 2 principal components. Oh, I see a typo. The one on the y-axis, of course, is the second component, PC2. But here you can see that there are clearly 3 clusters. The separation of the cluster is not perfect, but there are 3 dominant clusters which are rather well separated in the principal component space. And the question is, do they represent distinct electrostatic motif? The short answer is yes, and I will elaborate on this. But you see the size of the cluster. So we have the dominant cluster, cluster 1, more than 400 structures, cluster 2, more than 200, 3, almost 100. And in this cluster, there are subclusters that you can identify if you refine the clustering, and that is the number of clusters that you can find. Now, there is ecobonalities in the electrostatic properties among these clusters. The first row report examples from cluster 1, the dominant one, and the first two most abundant subclusters in that cluster there. And you see that generally the electrostatic potentials in this cluster are rather negative, and these are absolute electrostatic potentials with respect to the standard hydrogen electron. And see, they are negative. They look all the same, but there are differences in the symmetry of the localization of these negative spots, so they make the clusters unique. And in this family in this cluster, you can find ferrodoxins, dehydrogenase, and interestingly, high potential iron-sulfur proteins, the ones that have a very large reduction potential. And that is, I mean, in retrospect, it's obvious. To stabilize high oxidation states, you need a negative electrostatic environment around the cluster. In cluster 2, you have oxyreductase in general, again, ferrodoxin, dehydrogenases, but you start finding different classes of enzymes, the halogenases and others, which are not reporting here. And in cluster 3, you find very different enzymes, sulfide reductases, nitrate reductases, and so on. So it seems that, yes, in nature you have this hierarchical organization of the electrostatics of the protein scaffold that seems to be unique to some class of enzymes. Now you wonder, what are the features of the protein scaffold that makes these unique patterns? So we investigated many potential sources for this, and so we look at the surface accessible area of the cluster, the distance of the cluster to the surface of the protein, the total charge of the protein, the presence of positively charged residues, negatively charged residues within a radius, if I remember correctly, 12 angstrom from the center of the cluster, and so on, hydrogen bonding and so on. And we found that, okay, trivially, solvent exposure is important, but the charged residues around the clusters are some of the dominant factors for this variety of anisotropy of the electrostatic potentials, in according to the simple model that I presented at the beginning. Remarkably, hydrogen bonding have a marginal or a less important role. And so what is hydrogen bonded to the cluster? It is important shifting overall the potential, but it doesn't create these anisotropies or large shift as the other factors we have there. And if you look more into details to these major features that contribute to this electrostatic potential, you find that in cluster 1, you have that the cubane is typically close to the surface, and that you have an excess of negative residues, while in cluster 2, you have a nice balance, a more balanced distribution of positive and residues. In cluster 3, you have the dominant presence of positively charged residues around the cluster. So how much time do I have? 6 minutes. And so very briefly then, so these are just a macroscopic, if you will, analysis of the environment, how the environment influences redox potentials and the electrostatic property of the cluster. But the dynamics also plays a crucial role in that for fine-tuning everything. I want to give you a brief example of this, talking about iron-iron hydrogenase. These are enzymes that can oxidize hydrogen to protons and electrons, or you can reduce hydrogen and so on. So you can produce or reduce hydrogen. And there is this cubane filament here, 3 cubanes, that act as a pathway for the electrons in and out. If you are oxidizing hydrogen, you are releasing electrons, and they will go out from this path. Otherwise, if you are producing hydrogen, electrons will come from here, and they will form hydrogen. So we calculated the redox potentials for these cubanes using QMM simulations and classical simulations, using the scheme that Warshall proposed many years ago and Mikhail Sprick refined to ab initio molecular dynamics simulations. And basically what you do, you sample configuration with classical molecular dynamics, you open a quantum window around your cluster, you calculate vertical excitations energies, and within the Marcus theory framework, you can work out reduction-free energies and reorganization energies. You do this for the oxidized and the reduced and so on. So here is brute force. The more you sample, the better it is. But typically, we have a statistical uncertainty on the potentials of about 60 millivolts. So this is how we perform, more or less. In black, you have experimentally measured potentials through titrations, redox titrations. And there you have what we calculate. They are in the same range. What we notice is that the reduction potential of a cluster depends on the oxidation state of the others. And information actually that it is not available experimentally, and it was a priori not so trivial to say. And you can estimate also reorganization energies. We don't have experimental values for this, but there are 2 clusters that we observed that have the largest change, the largest reorganization energy. And it's interesting to see why, and as I anticipated, that is due to the dynamics, actually, of the residues around. So here, let me focus on the cubane, on the top panel. So you have the inoxidized cubane and the reduced cubane. These cubanes have lysines, so positively charged residues, as I told you so far, and so those are crucial for shifting redox potentials, but the conformation of these residues actually are redox depending on the oxidation state. You can have that the lysine is away or it is in close contact. So that is the origin of the large reorganization energy. But not only, so it's not clear at this stage if the positioning of the lysine is a consequence of the change in the oxidation state, or the position actually causes a change in the redox potential. And so, or maybe it's a mix of the two. And you can find similar situations also for other clusters there. So I want to conclude with an extremely important point, I would say, that the oxidation state of a cluster and what happens at the cluster strongly depends on the oxidation of other clusters, which are far away by 10 Armstrong or so. And here is the cubane that I showed you before, and the lysines that swings in and out. And this is a distribution of the position of the lysine that you can calculate from DMD simulations. And there are 2 curves. One is for the presence of a reduced cluster nearby, and one for the presence of an oxidized cluster nearby. You can see that the distribution is very different. And so the change in the organization energy and redox potential of this cluster strongly depends on what happens to this other cluster and so on. Think of very long chains, and so you have this effect, a long-range effect on a cluster that is due to faraway clusters. If you want, is a sort of electronic allosteric effect. And so you can have the same also for the other clusters, but I will omit this. And for sake of simplicity, I will also skip this, but just looking at the thermodynamics of electron transfer, you can also start thinking on how the electrons are delivered. And we found that actually the first electron is sparked on that cluster there, that it is not part of the electron transfer chain, and then the other electrons goes and they are delivered there. And so we are exploring now the idea that that small cluster there serves as a sort of rectifier for the electron conduit. So these are my conclusions, and we developed, I think, a very coherent framework just to rationalize the effect of the environment of proteins on redox properties of these clusters. We look at the electronic structures effect, electrostatic and effect of the environment, structural distortions. So we look into patterns in available crystal structures and so on. I want to conclude, of course, wishing an happy birthday to Michele. And many words have been said during these days about Michele and his mentorship. And I can only echo those comments. I want to add something. It's not just Michele's mentorship, which is, of course, crucial, but it is also the environment where you work, if you work for Michele. It's a very fertile environment, and you absorb knowledge, even if you don't want, just by osmosis. And so amazing, amazing. Thank you very much to all of you.
Thank you very much. We have used all the time, but we have 1 or 2 minutes for the questions, comments. Okay.
Yeah, thanks, Simone. Really, really interesting talk. So I have just a sort of curiosity. Is there any analog of these clusters in a sort of inorganic materials context, and if these iron sulfide, so to say, have ever been investigated, speak by ignorance, yes, as catalysts for the similar reactions?
Yes, yes. The answer is yes. And PNNL itself have efforts of encapsulating these clusters in synthetic constructs, self-assembled materials like peptoids and so on, to design microelectronic devices, right? And so all this study was also motivated by this, right? How we can tune the redox potential, so what kind of environment we want to have a given flow of electrons. You know, it's about thermodynamics, right? You shift in and out. And yes, and they have been also explored for catalysis, especially not iron sulfide, but molybdenum sulfides. And I think for the wrong reason, I believe, but people have been exploring them because in the hydrogenase you have also molybdenum, which is unique, is not iron, and so they thought that that was the catalytic center. It is not. So they try to encapsulate, in any case, molysulfides, for instance, in mesoporous materials like zeolites and so on. Yes, there is a huge effort in this regard.
Okay, question there.
Thanks, Simone, for the nice talk. 2 questions. Are counter-ions having an effect since the lysine motion is also important? Second, can you comment a bit more about mutations on lysines, how they affect the redox potentials, if any?
So yes, the presence of ions is important, especially for clusters which are exposed to the solvent, of course. And it can be dramatic, right? In the analysis that we have done, we haven't considered that. It was just based on a continuum model. But just to go back to your point, let me see if, just looking at what you have on the top part, that cluster is exposed to the solvent, is near the surface. And you can see when it is in the oxidized state, there are few molecules, but as you change the oxidation state, you have water pouring it. And of course, if ions are there and around the protein there is a cloud of ions, of course.
Okay, I see some hands on, but I think the time is there. I think everybody is hungry for the lunch. Now let's thank all the speakers in this morning again. Thank you very much.
The spin, yeah, I omitted that detail, yes, but spin is... I didn't mention it, yes, but it is, yes, it is there, and the reduced form of this cluster is... Those are very interesting. I already started a conversation with him, actually, about this.
Let me see, what kind of connectors they have here? Oh no.
This one?
Yeah, I definitely have to bring my switch for... Yeah, but I bring my iPad. I don't...
Pleased and honored.
5 minutes, I think, plus 5
Yeah.
minutes of discussion.
Let's see how. Ciao. Ali, you know how to Everybody knows how to connect my iPad to the. Wondering how to. Here
Yeah,
it is.
this one.
It was the wrong
Yes, here we are.
Vado a prendere il computer. Note, una roba. No, il PDF non. No. Poi convertirlo qui è un casino.
No.
There's a bit of technical problem, and we'll start 5 minutes late, okay?
Perde tanto risoluzione. È capitato con tanti iPad diversi.
Ma mesi fa non era così.
Non è sistemato, ma abbiamo il problema con tantissimi. Bene.
No, questo non mi ci vuole l'USB-C.
Ok. Ah, questa è l'alimentazione? Mai? No, sono i nuovi.
Mamma mia.
Li hanno rimessi, perché si sono accorti che l'USB-C ha problemi. Hanno fatto passi indietro. Meglio proviamo.
Vada.
Allora, sì.
No, vederlo qua, no, vedere
Sì.
qua.
Le note del
Mirror, no, non mi
allora
serve.
è giusto, va bene.
Usavo questo come pointer, però
Le do per muovere. Sarebbe se si può, ecco. Allora è acceso, allora noi possiamo fare così. Come presenter, perché come pointer lo do un laser, perché se no quelli digitali bisogna avere tutto il software. Non le do un presenter, così può cambiare lo slide.
Qui posso andare avanti e indietro? Sì. Stupendo.
Ce lo proviamo, ce lo troviamo un altro. Può essere che il sistema chiede di autorizzare di uscire un attimo da fuori il momento.
Cosa devo fare?
Allow. Ok, questo può anche chiudere.
Vado via, quit?
Vediamo. Ok.
Stupendo.
Avanti e indietro, destra e sinistra.
Destra e sinistra, avanti e indietro. Ah, questo è il pointer.
Sì, sperando che abbia un po' di...
Sì. E sotto che roba è?
Per uscire, no?
Ok, stupendo.
Okay, our first speaker is, Stefano Baroni. Everybody knows Stefano from CISA. And he will talk about invariance principles in the theory and numerical simulation of heat transfer. So please.
Thank you, Carmen. So the title, meanwhile, has slightly changed, but the content has no. has not, so I will talk about the same soup. Let me start, as usual, by thanking Ali and all the organizers for inviting me, and particularly Michele for consenting to having me with you today. There is nothing to laugh. I am at the court of the king has to agree to the...
I gave only very generic thing, and you are an exception to that I wanted to have as much as possible young people and women in science. That was my generic.
Which I am not, either.
I mean, okay, sorry. The other,
you know,
then they choose it.
Okay. Thank you.
I'm very
in
fine
any way. That's like the chernia. I don't know how these big fishes are called in English. So they transition sex at a certain age. So they are born a male and turn a female, or the other way around. So this may have happened to me as well. Thank you in any case. Thank you in any case. So this is a quote that was brought to my attention by my friend Davide Donadio, due to nobody else than Rudolf Peierls, who once said in early 60s or so that it seems there is no problem in modern physics for which there are on record as many false starts and as many theories which overlook some essential feature, as in the problem of thermal conductivity in non-conducting materials. He actually said non-conducting crystals, but I've taken the liberty to correct it because glasses are even more surprising and even less well understood than crystals. So how I got involved in this business, it's kind of strange. I was visiting Giulia Galli some 20 years ago when she was still in Livermore. And I was invited there to talk about excited states through density functional perturbation theory, time-dependent density functional theory, and the stuff I was most interested in at the time. And I was very surprised to learn from her that at the time, nobody really knew how to simulate, how to compute thermal transport from ab initio molecular dynamics. And I was very intrigued by that. And the problem stood in the background of my interests for the following 10 years, during which, working very occasionally from time to time, I developed a formula for the DFT energy current, and learned the very basic rudiments of statistical mechanics, which I was not very strong about, that were instrumental to use the formula that I had developed. So this is the main framework I will be working in. So this is the formula of the heat conductivity, or of any transport coefficient for that matter, in terms of the autocorrelation function, the integral of the autocorrelation function of some suitably defined conserved current. the relevant current for heat transport is the energy current that is defined, that can be defined in terms of atomic energies that are very familiar to all of you nowadays, because it is exactly in terms of those atomic energies that machine-trained potentials are defined. But at that time, it was not as popular as they have become now, but still they were an essential ingredient for the definition of the energy current, as well as their derivatives with respect to nuclear coordinates that go into the so-called virial contribution to the current. So little after I learned about these difficulties from Julia, one of many similar papers appeared stating that the widely used Grimm-Kubo relation, that is this one, this one does not serve our purposes, that is to compute the Grimm-Kubo formula for the conductivity, because, so it was believed, in first principle calculations, it is impossible to uniquely decompose the total energy into individual contributions from each atom. In the next 10 or 15 minutes, I will argue that such a uniqueness is not necessary. Actually, it is not unique, the decomposition. Nevertheless, the resulting conductivity is well defined. And the difficulty, furthermore, is not restricted to quantum simulations, to ab initio molecular dynamics, but it is a general difficulty that has a general solution valid both in quantum and classical frameworks. So how come? How is it that density functional theory, that is a formally exact theory of the electronic ground state, cannot predict all the measurable adiabatic properties, all properties of the electronic ground state? So this is the picture of a famous picture of the last blackboard left by late Feynman at Caltech, where he was lecturing. And the sentence that I would like to highlight is the first one in the upper left corner, where he said that what I cannot create, I do not understand. And of course, he meant what he said. He did not understand, admittedly, quantum mechanics, and he reinvented it through path integrals and stuff. So of course, I am no Feynman. I am not able to create anything, but I've spent all of my life computing stuff. And I would argue that what I cannot compute, I do not understand. If you cannot compute something, it is that you really do not understand what you are aiming to compute. So just a very brief preamble. So starting from Fourier law, that is the definition of the thermal conductivity as the ratio of the heat flow over the temperature gradient. We have seen already the Green-Kubo formula. You have a quantity, the current, that decorrelates at a large time, so the autocorrelation function decreases in the large time limit, and its integral saturates sometimes, not always. If the conductivity is finite, it saturates to a value that is the conductivity. By using the same algebra, that led Einstein in 1905 to establish the relation between particle diffusivity and velocity autocorrelation functions. Helfand in the early 60s argued that this Green-Kubo formula can be reformulated in terms as the ratio of the variance of the integral of the current over time. As in any diffusive process, the variance of the displacement increases linearly with time, and the ratio between this variance and time is by definition, not by definition, by algebra, I would say, the autocorrelation, the conductivity as expressed by the Green-Kubo formula. So just to recap the classical framework, so the transport theory is a theory of fluctuations of hydrodynamic variables. Hydrodynamic variables are densities of conserved quantities, such is the energy. And by doing some algebra, which I will not go through today, you can easily see that if you have an energy expressed in terms of local contributions, of a local representation, you can express the current in this way. Now, let us play a simple and dirty trick. So you take this expression for the local energy, and you modify the potential contribution by multiplying by 1, which makes nothing, plus a matrix gamma ij that is arbitrary, other than for the fact that it is antisymmetric. Because gamma is antisymmetric, the potential energy is symmetric, the sum over all the pairs goes to 0, so the total energy does not depend on gamma. You repeat the algebra that leads to from the decomposition to the current, and you learn, rather surprisingly, that in spite of the fact that the energy is the same and does not depend on gamma, the current does. What happens if you apply Green-Kubo to the modified current? Here is a simple Lennard-Jones liquid with gamma chosen rather arbitrarily in any way. You choose anything that is antisymmetric, and you see that the autocorrelation function does depend on gamma, just suggesting that the conductivity may also depend on gamma, which would not be a very pleasant situation, other than for the fact that the integral does not. How is it? You do a little bit of algebra again, and you realize that the extra term that is proportional to gamma is actually the total derivative of a vector that is bounded in phase space. If you apply now the Einstein-Helfand formula to the modified current, that is the original one, plus the total derivative, you do some very simple elementary calculus, and you see that because P prime is a total derivative, you can integrate exactly, and because it is supposed to be bounded in phase space, you see that the variance of P of t minus P of 0 is actually bounded as well. You put it in the formula, in the Helfand-Einstein formula, and you see that the first contribution to the variance is the original conductivity, what you are after. The second one, the variance of delta P, is bounded, and the covariance, because of the Schwartz identity, goes like the square root of the two variances. One is proportional to T, the other is constant, so the covariance grows as the square root of T. When you divide by the time to implement Helf and Einstein, you see that those terms that are crossed out do not contribute, and therefore the modified conductivity is equal to the original one. So is this a general property or was just an accident due to the particularly silly way I have decided to modify the breakup of the total energy? Well, we go through some simple thermodynamics. We all know that energy is additive, but actually it is only additive in the thermodynamic limit, because if you have two finite systems, the energy of the juxtaposition of the two systems is not just the sum of the energies. It is the sum of the energies plus some interaction energy. The interaction energy doesn't matter in the thermodynamic limit because it scales as the volume to the 2/3. So in the thermodynamic limit it does not matter. But if you are to define an energy density, a microscopic breakup of the energy, so you have to assign an energy to an infinitesimal volume, or for that matter to an individual atom, and in that case it does matter how to decide to partition the interaction energy between the energies of the two subsystems. So the new energy is equal to the old one, but for terms that scale as the interface between the two. So this scaling as the interface is like the scaling of the integral of the divergence of a field. So the integral of the divergence of a vector field is something that closes at infinity, and at infinity it doesn't matter. So if you add to the energy the divergence of a bounded vector field, the total energy wouldn't change. Energy conservation implies, if it is conserved locally, a continuity equation. You plug this relation, this gauge transformation, into the continuity equation, and you see that the current, the microscopic current, is modified by a term that is the total derivative of a bounded vector field. You integrate it, and you get what you need for invariance of the conductivity. So any two conserved densities that differ by the divergence of a bounded vector field are physically equivalent, and the corresponding conserved fluxes differ by a total time derivative. Therefore, the transport coefficients coincide. So the solution to the problem is actually very simple. Like in electromagnetism, you don't really care about the gauge. You just choose one, the one that is best suited to your purpose. You close your eyes, you crank your computer, and if you are good enough, fluctuations may depend on the gauge. So you have to be careful, but this is also a blessing, because you can choose the gauge in such a way as to minimize the fluctuations. If you are not so good, you will be killed by fluctuations. If you are clever enough, you can leverage gauge invariance to reduce fluctuations. A very brief detour that is needed for the conclusion of my talk to what happens in a multi-component system like a grappa, 50% ethanol, 50% water. Here you have two relevant conserved quantities, energy and the mass of one of the two. The mass of the other doesn't matter because the total mass the flux of the total mass is momentum that is conserved, and you have not to care about it. You don't have to care about it. So in this case, you have to use a multivariate version of the Fourier law that is embodied in Onsager's formula for the coupled transport of many conserved quantities, and you end up with a formula that has to be kept in mind for the next 1-2 slides. The conductivity is, the thermal conductivity is defined as the energy flux when all the other currents are at rest. So you have to solve for the Onsager system in the case where Jm, the mass current, is equal to 0. You impose J equal to 0 here, and you get a formula for the conductivity that is no longer the autocorrelation function of the energy current, but is the inverse of the diagonal element of the inverse of the Onsager matrix. So you have to compute both the autocorrelation functions of the energy, of the mass, and the cross as well. It is interesting to see how this can be achieved in a numerically efficient way, but I won't have the time to go into this. So here, the one thing that I would like just to highlight is that these two, lambda EE is different from kappa. These are the power spectra of the energy current and the power spectra of this reduced so-called Schur complement of the Onsager matrix, and you see that in the low frequency limit where these spectra give the transport coefficient do not coincide. So contrary to what is often assumed, the heat conductivity is not the Green-Kubo integral of the energy current, but this slightly more complicated formula that requires a multivariate analysis. An important consequence of this that I would like you to buy from me just on my good faith. It would take a few minutes to demonstrate. But is that this formula for the conductivity is invariant when you add to the to the energy current any linear combination of mass currents. So you take instead of the energy current a linear combination of it and any mass currents. You plug it into this Schur complement formula, and the transport coefficient remains the same. So this is another invariance property that we had nicknamed convective invariance, because these mass currents are actually convective currents. So this is the impact that this has in modern molecular dynamics simulations based on neural network potentials. You take two different models for two different trainings for your neural network. You get a power spectrum of the energy of the conductivity that depends on the model, but the small frequency limit that is the static conductivity does not depend on the model. Rather meaningfully, instead, you see that the energy-energy correlation function does depend on the model, and both models give values of the Green-Kubo integral that are way off the actual heat conductivity predicted by the potential model. So I would like just to summarize what are, so far I have kind of introduced what the problem is and not yet given the full solution. I think everybody's expectation is that the measure of the quality of a potential model is that it has to give the correct forces, right? You have a training set that is built, generated with whatever level of theory you have. The best you have, the better it is. And the quality of the model is that the forces have to match the ab initio forces. Then two models that give the same forces on a physical basis have to give the same conductivity. Is this the case? I will show in the next 2, 3, 4 minutes that this is indeed the case, or at least I think it is, and give you a few open problems. So here is the definition of the force, that is the derivative of the sum over all the atoms of the atomic energies. That is, I can express the total force acting on atom I as contributions due to all the other neighboring atoms. So the condition that two models give the same force, the same forces, is equivalent to the condition that the sum of the differences of the forces, of the local representation of the forces predicted by the two models have to vanish. The total has to be the same, the difference has to vanish. Is this enough to guarantee equality of the transport coefficients? Well, we go through the algebra, and we see that we can express the difference between the currents between with the virial contribution, that is this one, where here we have the difference between the forces. So the primed quantities are differences, and what remains of the convective term. Here I split explicitly the atomic energies in the value they would have with all the atoms removed far away, one from the other, that is the energy of an isolated atom, and the contribution due to the presence of all the others. Now, I won't give you the details of the demonstration, but you can show that under the condition that the sum of the atomic contribution of the localized contributions to the atomic forces vanishes, that is the condition that the total forces coincide, and if all the forces are short-sighted, which means that the force acting on atom I due to atom J vanishes when the distance between I and J is large enough, which is usually the case in machine-trained neural potentials. Then you can demonstrate that the sum of these two contributions to the virial term is independent of the path. That is, the integral is the integral of a conserved quantity, and is periodic in the upper limit of integration. Periodicity is key now, because when you do the integral here, you have the integral of this term here that is periodic and hence bounded. Therefore, when you plug it into Einstein-Helfand, it doesn't matter. So you can forget about this. The integral of the isolated atom contribution to the convective term does contribute to the energy-energy correlation function and the integral of the energy-energy correlation functions, but because it has the same structure as a mass current, you can think of this if these EI were masses, these were convective currents. And we saw before that the mixing of the energy current with any convective currents wouldn't change the conductivity. So the two conditions that the forces coincide and that the neural network representation of the energy is short-sighted guarantees that the heat conductivities coincide, whereas the energy-energy Onsager coefficients may not in general. So here are my conclusions. Different local representations of a system's potential energies. Sorry for. So I had corrected I have the conclusions on the iPad, but the iPad doesn't work, so the conclusions are not what they were meant to be. So let me just. No, it's the same. It's the same. It is the grammar here is wrong. So it is ill written. It is not well written. So let me recite them aloud without reading, not to get confused. So different local representations of a system's energy give rise to the same heat conductivity. The resulting energy-energy correlation integral does depend, or may depend, on the gauge, on the specific representation of the neural network, but as said, the properly calculated heat conductivity does not. Therefore, the correct multi-component formula for the heat conductivity must always be used when computing thermal conductivities of a system with diffusing mass currents. That's compulsory. It's not an option. Otherwise, the result would depend on an arbitrary shift of the atomic energies that does not affect the forces. So that would be admitted by physics, but it would give. You have to subtract it, that contribution, from the transport coefficient. On my iPad, I had a last bullet that was saying that I expect that similar conclusions would hold for long-range forces, where this hypothesis that I had used does not hold. But to tell the truth, I do not know why. So when Michele will turn 120, I will give you the explanation. Hopefully. So some thanks particularly to the many people I have had the privilege to meet and collaborate with in the past 10 years of my scientific life that have been busy mostly with this kind of stuff. And let me conclude just with a few words about Michele and my long relations with him. Some 10 years back, I think we were in Chicago. I was invited there by Julia to attend the CPMD conference. And Michele raised his hand and said more or less, this is the best stuff you've ever done. And which is a kind of sweet and bitter statement. So I think it is a true statement. I know. I know you could think bitter things, but never spell them out. So you spelled out the statement. I knew for sure it was sweet, and I know for sure that for a change he was right. I do not know whether to regret having waited so long to give my best, or to rejoice at having done so at the age when many of our colleagues lose interest in science. Either way, this has been the project that taught me the most, and one that I would hardly have believed I could handle when I was at the age when I met Michele, too long ago to remember. Michele's outstanding creative longevity has been and continues to be an inspiration to me, as I'm sure it will be to the many generations of outstanding scientists he has raised. Thank you from all of us, Michele.
Thank you, Stefano, for this excellent talk. Questions?
Thank you, Stefano. We need a couple of months to digest your beautiful lecture. This work relies on the green cubo, so in linear response regime. Is it in your head already how to go in the non-linear regime, for instance, to treat, I can think, for instance, of laser heating of materials?
You know, I am a linear man. I'm a very simple, I am a simple person, and most of the things I've done are linear responses. So this is what I can do. I will keep thinking about what you say, but I don't promise anything.
I have a question about the last part you showed on the consequences of having different machine learning potentials should give the same thermal conductivity, of course, or transport coefficients for the matter. Unfortunately, the FI, let's say, the difference in the so the assumption, you do the calculation for assuming Fij is the same, right?
What do you mean?
So you are assuming you say, oh, the error, if I get the same...
No, it's not symmetric. If this is what you mean, I'm not assuming Fij is symmetric.
But there is an error propagation in fact.
From where to where?
From the differences in the machine learning models, there is an error on the forces, right? And that error on the forces propagates to the transport coefficients. So the identity is an identity with an error.
Sure.
And do you know, did you calculate how it propagates? Because it can amplify the differences enormously.
Never done. That's interesting. But what I know, I have no theory, no mathematics, nothing even vaguely rigorous to say. But I know for sure for reasons that I do not know, that transport coefficients are rather insensitive to the details of the forces. Let me tell you, so when in one extreme case, we did it ourselves, my collaborators and I, at the start of all this. We computed the thermal conductivity of a fake DFT argon fluid. Fake because if you do, it was a local density, something very wrong for argon, for a Lennard-Jones fluid. But just for the sake of comparing the conductivity computed from DFT, which we were very excited about at the time. We had this brand new formula that we wanted to test it, and we tested it against a Lennard-Jones potential fitted to the DFT trajectory. It was very wrong. The conductivity was spot on. There are even more blunt, there have been more blunt attempts to fabricate theories of heat conductivity some 10 years back. I will not quote the authors because I rejected the paper that was given to review to me. But there were those who claimed that the right way of computing thermal conductivity from first principles was exactly this, to do a first principle ab initio molecular dynamics of a complex system, not the stupid pseudo-argon stuff, and then to fit a two-body potential that is very wrong. And the thermal conductivity that was published, that I didn't doubt that it was faked. I think it was the result that it had to be, not spot on, but not very far from. So I think heat conductivities are, at least to me, have been conceptually hard to understand. It took me many years just to make sense of all of that. Not totally sure I've made sense even now after all this time.
I second that.
But,
being in the business.
but in practice, they are tolerant to errors.
So I'm first. So what about the energy momentum tensor? After all, energy mixes with momentum flux.
No, because of symmetry. Energy is a scalar.
In relativistic theory,
I
it
see.
certainly does. Huh?
Sure.
And this covariant constraint gives special relations.
We were discussing about retirement, Michiel, right? I'm going to retire soon. I know what to do for the next 12 months.
In my retirement, I read this book called Classical Field Theory by Iron-sulfur. I can strongly recommend.
I will. I will follow your recommendation. Thank you, Michiel.
Thank you for this beautiful talk, Stefano. But
ciao, Ali. Good to see you.
I had a question. So in your initial quote, you emphasized non-conducting materials. So then the question that arises is, suppose you have a system where the electronic gap is becoming small, and then the conductivity is presumably going to be heavily influenced by, electronic conductivity and so on. So the question is, how, or does this formalism translate into that sort of situation, or we need something totally different?
The short question is, I don't know, but I have a few feelings that I may try to share with you.
So a full quantum formulation of transport is difficult because you cannot, at least I do not know how to do real-time simulations of a quantum system. So all this green cubo stuff is conceptually very clear how to do, but you have this integral in the complex time path that I wouldn't know how to simulate in practice on a computer. So the first half of the question is I don't know exactly what to do, but I think that the general idea of this gauge invariance has to hold in a way or the other, because it is due to a property that is not pretty classical. It is general and quantum mechanical as well, and that is the combination of two things. That is energy conservation and energy short-sightedness. So if you combine the two, I think that any quantum mechanical expression you may devise of an energy current, I think it will continue to be intrinsically ill-defined, but the conductivity that you compute, or that you may compute if you know how to, from it has to be independent of that microscopic representation, both for physical reasons, because it is measurable, so it cannot depend on the way you do calculations, and also for mathematical reasons, because the ingredients are the same.
There are more questions, but I think for the benefit of the time, we will move on to the next speaker. We thank Stefano.
I forgot.
Okay. Quickly.
Okay, happy birthday.
So the next talk is by Roger Rousseau. Roger was a former postdoc of Michele Parinello when Michele was in Stuttgart, Germany, end of the 90s. And now, then he worked in the Pacific Northwestern National Lab. He was also spent quite a lot of years here in CISA. And now he's in Oak Ridge National Lab. And Roger will tell us about the effect of collective dynamics and anharmonicity on entropy in heterogeneous catalysis, building the case for advanced molecular simulations. That's the longest title of the
I use ChatGPT. Okay. Just made something up. Well, actually, so I need to say that, about 10 years ago, as we were kind of restructuring our catalysis program at PNNL, I decided that we needed to really spend more time learning some of the methodologies that Michele was inventing in Lugano. And we had many trips there every year. It was very much enjoyable. And we talked about all of these great things and the reasons why you needed to do statistical mechanics and catalysis and get away from some of the very simplistic ways people were trying to understand this. And in fact, the work, it was like going to an all-you-could-eat buffet of science. It was just so much, and it was so great. And every year you'd go, and there'd be something new. And this still continues to this day, because we went back about a year ago to Genoa, and the team is doing wonderful things. So as I've been sitting in the back up there, I was thinking to myself, how am I going to do better on this topic, which is something I've talked about for decades? How am I going to do better than that? So I decided I'm not going to talk about this. Now, because I had to clear that with the US government, that is still my talk title. Okay, so I don't have to go back and wait 2 months to get cleared to do this talk. Okay, so I'm going to do this one. So this is a kind of thing. So I'm going to talk about catalysis. I am going to talk about something that's a bit bizarre, might be a little too much chemistry for this room, so please forgive me. This is going to be a bit of a chemistry talk. Let me explain the title. So everybody in catalysis says, oh, single atom catalysis is going to save the world. We get these small atoms, and you don't need high metal loadings. You'll be able to do great science. The other thing they tell you is it's a perfect analogy of an organometallic compound, and we'll be able to do great science with that. Okay, here's the issue. Those things are not blanket true. And in fact, the last one is completely untrue. Because if you do single atom catalysis, if you're not maybe doing some exotic electrochemistry with atoms buried in a carbon film, for the most part, you do reductions and it fails, okay? It's something intrinsically unstable, but if you try, which is something organometallic complexes are very good at. On the other hand, if you try to do oxidations with an organometallic complex, it'll get eaten. So, in fact, the two do completely different chemistries. And so the question was, about 15 years ago, we started to put together a CO2 conversion program at PNNL. And the idea was, can we induce new chemistries to try to do reduction reactions with single atom catalysts? And I'm going to show you that we can. But first we need to understand the rules of the road of how to do this. Okay. So before I get into that, just wanted to thank all these wonderful people that we've had. Okay, so that one there was adopted. I'm just going to say it. Giovanni Maria was with us for a few years. These are the people who contributed to this. A lot of the work we've seen is this smattering over the years from both fundamental catalysis projects and applied catalysis projects at PNNL. And some of that work is continuing on at Oak Ridge with Vanda. And a lot of that was generously supported by the Department of Energy. And we had experimental collaborators. So when you're going to probe a complex system, theory is there to actually give you guidelines. If you do it in real time with experiment, you can actually really drive the discovery by in-time hypothesis refinement. You push each other. I'm going to show you how this works. So before I do that, I just want to give a little bit of, this is my current thing. I'm no longer doing catalysis. I no longer actually am a researcher. So I am now at Oak Ridge National Lab. It's a very different organization. It's a legacy from the Manhattan Project. We are the original division that learned how to do chemical separations for the atomic program. We learned how to separate plutonium and uranium. Chemical separations is still our strength. We're a very large division. We are separated into 3 groups, which is fundamental chemistry, more interfacial, materials chemistry, and nuclear analytical chemistry. So these are our strong suits. And we still are very much focused on chemical separations and a little bit of catalysis. What is really nice about this is, unlike other places in the DOE, we're not stovepiped at all. We're fully integrated between fundamental and applied, which is something I need to mention for the next talk, in that I always kept 1 foot in the fundamental, 1 foot in the applied. We always kind of worked back and forth between the two. It actually is a great environment if you really want to use fundamental science to actually drive something that might actually have a productive use for society. Okay. So this is what a real catalysis project looks like. Okay. So this is, first of all, catalysis is kinetics. So if you're doing free energy simulations or complex simulations, that's all wonderful. It can give you some insights into the thing. But if you really want to connect to what's really going on, you need to understand that you're not at equilibrium. It is a kinetic process. So we need to understand kinetics. So all that information we gather from simulations ultimately needs to go into understanding a kinetic model. Okay, so the problem is that the catalyst is not the thing you put in there, it's the thing that forms under reaction conditions. But you're not at equilibrium. So depending on what your kinetic conditions look like, whether you're in a batch reactor, whether you're in a flow reactor, whether you're running at differential conversion, or you're doing what they do in industry where they're running at full throttle, and the front of the reactor and the back reactor look very different, so that means you have different catalysts at different parts in your reactor. You need to understand that because this is the reality of the real system. On top of that, you rarely have, so this is the same catalyst, this was one that we were developing at the time to do syngas conversion from biomass into what we call C2 oxygenates. It's something that you can very quickly hydrogenate into the starting material for something like jet fuel. And in fact, actually, as I was leaving P&L, the next catalyst in the loop was something we were commercializing to go to, because you can take the ethanol that would come out of a catalyst like this, and you can start making butenes, and then butenes are one step away from jet fuel. Okay, so you really want to understand the limitations. So this is a snapshot. We had two catalysts, both of which had very high productivity. One was on a silica support, and if you run an ab initio MD simulation, it looks like that. There's like oxide pieces on there. There's everything. It's a soup, okay? These were simulations done about 15 years ago, by the way. That one, the one on the carbon support, actually is in a much more reduced state. You don't have oxidized metals, and it's actually a completely different shape. Okay, that's what it looks like at the front of the reactor. At the back of the reactor, because this was run under industrial conditions, you're basically, the catalysts are swimming in water, and the oxide catalyst is basically completely inactive, and it's just chunks of oxide everywhere. And the reduced catalyst is doing something else. Both of them do conversion, which so whatever the active sites are on these catalysts, they still survive no matter what form they're in. And you need to actually try to get your hand around that. Okay, so those are the rules of the road. So we need to really be a little respectful of how difficult these systems are. We need to take them apart. We need to use every bit of our understanding. So we're going to work with model catalysts, and we're going to do very simple reactions. It's not the reality of doing a truly catalytic system. Okay, so we're going to start with work that I did shortly after coming from Trieste to P&L, just looking at reducible oxides. These are oxides where you have redox capacity. So in iron, you can go iron 2, iron 3, so you can do redox chemistry, so you can transfer charge to and from the actual surface. TiO2, you can have titanium 3+, and things like ceria, you can have ceria 3+, 4+. A lot of this was inspired by the absolutely amazing work that Annabella has done on polarons at surfaces, and we wanted to ask the question, how do we use this for catalysis? One of the interesting papers we did over the years with surface scientists was also to understand how much the defects in the bulk versus the surface matter. And in the end, it turns out the surface within about 1 nanometer is what you need to understand. So the charge carriers near there really control catalysis. This is one of the keys to understanding what I'm about to show you. Okay. Simple process. I'm going to put a nanoparticle on top of the surface. Okay? Now, I can have charge carriers in the surface, I can have charge carriers in the nanoparticle, and I can have molecules coming down on the surface, maybe on the nanoparticle, maybe somewhere else. And it turns out that because these charge carriers are mobile, and you create electrostatics, which are also long range, at least operate over about a nanometer or so, you end up with a situation where everybody's coupled. So I can take a TiO2 system, I can put a gold nanoparticle on that, and I can look at the work function as I just put oxygens down on the surface. If I have a deficient, electron deficient, so if I say have oxygen vacancies on the surface, I have these excess charge carriers, some of them can end up in the gold. The gold is negatively charged, and you can see that as a shift in the work function, it actually gets lower. Okay. You can have a neutral system where there's maybe no excess charge carriers, or if I over-oxidize it, instead of having oxygen radicals on the surface, you can pull electrons out of the gold and transfer them over. So what happens is you can get charge swings. And we actually show in this paper that impacts the dynamics, it impacts a lot of different things. For the purpose of this talk, though, I want to talk about what it does to chemical mechanisms. Okay, so this is a mechanism that was proposed by, I believe, Jens Norskopf. I'm going to call it the Langmuir-Henschel-Wood. It basically, your CO2, or CO comes in, it binds to the gold nanoparticle. It turns out it can move around fairly freely on that surface by just dragging around a gold atom. Put some oxygens down. Okay, so then that CO, can come down, grab one of the oxygens off of the O2, flies off as a CO2, and then you repeat. Now, I have two different versions. I've done these calculations where the surface is basically fully oxidized, no extra charge carriers. And in the other case, I've done it where I have not scavenged all the charge. And what you see, so the numbers in the circles in the middle are the actual total charge on the cluster. And the numbers on the outside are actually the energies of the reactions. And what you see is that the numbers change for reactions where electrons are being pulled from the surface to the molecule. And in fact, when we started looking at the literature, we realized that everybody was getting different numbers, but there were really only two classes of numbers. So a lot of numbers in the literature that people were attributing to, shall we say, sloppy DFT, was in fact that people were using physically different models of the catalyst, and in fact both behaviors were possible. So you have this charging and discharging. It also means that your surface is acting as a chemical potential of electrons, and it is having a huge impact then on the energies of these reactions. Okay, so in the same way that pH can control the rate of, the amount of proton transfer in a liquid, and it kind of anchors a liquid to the bulk pH, the charge state of your surface here does the same for catalysis. Okay, so I'm not going to talk about the first one, but let's just take a look at, this was found during ab initio MD. It was found on both Syria and TiO2. The catalysts are very dynamic. You've seen some talks, I believe, earlier on Monday showing this similar phenomena on magnesium where you have a lot of dynamics. What we found is that you would have these add atoms shoot off the cluster. They're not attached to the cluster. They would run out, and if they had a CO on it, you could actually very easily pick up an oxygen. Okay? Then, of course, that would fly off as a CO2, and you would get a vacancy. So if the add atom goes back into the cluster, then you're fine and you can go on to the next one. If the branch point is if the add atom falls in the hole, it's basically dead. It's catalytically inactive. And in fact, if you look at the TEM of dead catalysts for gold TiO2 that they use in firefighter masks, you actually see single atoms kind of everywhere. So those are the dead ones. Those are not the active ones. Okay. So turns out, though, that, again, those reactions are dependent upon the energy of the surface. So we need to factor that in to understanding the kinetics of the model, because that means as you have molecules on one part of the surface, it's going to impact the energies of the reactions, and this is going to have an interesting impact on mechanistic pathways. So, okay, this is catalysis. I'm going to introduce the concept of microkinetics. It's not hard. So I'm going to take all those reactions, I'm going to write a table. This is a very simple mechanism. I'm not saying I've solved the mechanism of gold oxidation. I've gotten past that. You're never going to be able to get that. You might find a few new tricks. The reality is that the systems are very dynamic, but I want to understand principles. Okay, so these are kind of the 10 basic reactions that we found. We can write them out. We have to factor in that different sites and different redox states actually impact different, have different barriers because that changes. You can write out a catalytic mechanism, the orders of the reactions that'll get you back to a starting point. And what you see is that these reactions, there's more than one pathway to go around the circle, right? I can go around the outside, I can take multiple shortcuts, I can go across, and of course, because if you assume that there's an equilibrium, you can have those errors going either way. So the question is, what's my mechanism? Here's the answer, and this is always true. There's always more than one pathway from A to B. Some dominate under certain circumstances. So I need to understand that what I'm going to do is I'm going to set up a series of differential equations, and I'm going to propagate the flux on that network, and I'm going to see which of those, shall we say, reaction channels become the most dominant. Okay, and here we go. So it's kind of like, I'm not going to say phase diagram, but it is. This is, I have two variables. One is my oxygen partial pressure, because that really controls the number of charge carriers I could have at the surface that will scavenge up electrons or not. And the other is temperature. And what we see is, depending on those two variables, even with a very simple kinetic model, which is a gross oversimplification of this system, you see that you have very different mechanisms. Okay? And the one that's dominant at low temperature is this single atom one. So this one where the catalyst shoots out an atom, it grabs something off the surface, it goes back in. At higher temperatures, the one that I denoted Langmuir-Henshelwood, the one on the perimeter of the particle, dominates, but not, I mean, you can see it's complicated. And this one LM in the middle is actually a hybrid, where the first step is done on the outside of the cluster, and the second step is done by an atom. Okay, so you get all kinds of different pathways, and these are the dominant ones. The other pathways are also active, they're just not as active. Okay, so the reality is you get a zoo. So if somebody tells you, I'm going to sift a catalyst by looking at a mechanism, just smile. Because you're only going to find the catalyst that does that mechanism. You're not going to find you're not going to actually understand catalysis, because the reality is the mechanisms are much more complicated. So is there any truth to this? So it turns out there's this really great review by Wayne Goodman, okay, the late Wayne Goodman. And he has this table of all the catalytic measurements ever done up to that point. And you look at that table and you go, oh my God, it's like a bug on a windshield. The numbers are everywhere. So that means as a theoretician, that means I'm in agreement with anything I want. I always have proof. It turns out that it's actually much more subtle than that, because when you start looking at those numbers and you start putting them into bins, you realize there's really only two numbers. There's the numbers for activation energies. So what I'm going to do is I'm going to look at the temperature dependence, and I'm going to plot, just like you do an experiment. I'm going to take my kinetic model, and I'm going to plot the temperature versus 1 over T, so my rate versus 1 over T, and I'm going to actually look at the slope of those, because that's my activation energy. That's the one thing from a catalytic mechanism that usually is transferable. The entropies are not, because they depend on a lot of subtleties about the experiments, but at least I have something to compare to. And it turns out there's really only two numbers. Out of all of those tables, there's two numbers. And if you look, there's a low barrier version, which actually comes when the surface is reduced, and a higher barrier when the surface is fully oxidized. And this model actually completely reproduces that. Okay, and these numbers are actually in relatively good agreement. I mean, as good as you'd expect for DFT, and I'm not going to quote the exact number, but it's in our paper. The point being that it tells you that there's a lot of complexity here. There's even a couple of measurements, by the way, where they left the catalyst going long enough time on stream that the whole surface became oxidized. So it went from an activation energy that looked like the first one to an activation energy that looked like the second one, which was kind of also a very comforting thing. So we knew that we had different mechanisms in different places, and it was consistent with the model that we had. Okay, what's the main take-home? The state of the surface can be used to change the chemical pathway. Can I use this now to take this thing to go do the chemistry that single atoms are not known to do? They're cations. They normally do oxidations. They do not like to reduce anything. So I am going to show you how we came up with an idea to actually flip this. Okay, And it started with a very simple surface. This was the perfect thing to study, except for the fact that it's iron oxide. Anybody who's ever done calculations on iron oxide knows it's bad. So we teamed up with Gareth Parkinson, who was working in Uli Dieber's group. I think he's still there. And they'd just done this beautiful works characterizing the surface of magnetite, where it's a slightly over-oxidized surface in the parlance of what I'm saying, because it's actually deficient in metal sites. It's excess of oxygen. And basically, it's got these very nice vacancies at the surface, and it's well controlled, and it's perfect for surface science measurements, and it's living hell to do computationally, because you have to really pay very close attention to basically controlling the magnetic superstructure if you want anything that's even reasonably close to experiment. So we used a DFT plus U, really wonderful work done by Man Thuong, who was a student here at ICTP. We nicknamed him Superman because he really knows how to get it. So again, I said the surface is over-oxidized. We put a palladium atom down. We looked at it experimentally. We put an alcohol down, and sure enough, it does exactly what you would think a single atom would do. It oxidizes. So turns out the surface would love to chew up alcohols, but it does so very slowly, because if you put it on the regular iron oxide surface, there's a giant barrier to actually stripping the aldehyde apart, or the alcohol apart to make an aldehyde. So the relative yield is very low. Okay. You put the single atoms down, and we know we can see them as single atoms. We check them in STM. And sure enough, what happens is the barrier for actually pulling the thing apart is very low, and then it can move off onto the surface, so you can start building up aldehyde and eventually acid on the surface. Okay, so this surface is not good for reducing CO2. This surface is good for oxidizing, so it's good for burning stuff. It's good for making CO2. How do we flip that? Okay, so let's take a look at the metal. Okay, so I had a palladium atom there. So we noticed that the palladium atoms can activate hydrogen. You put hydrogen down on the surface. If you put it down on magnetite on its own, you don't do too much. Okay, it's not very good at activating hydrogen. You really have to crank the hydrogen, crank the temperature. You put a metal atom there, it's actually really good. It splits, and then you suddenly get hydroxides, and you have less iron 3s at the surface, you have more iron 2s. So we studied this in STM, and we actually saw that, okay, a metal atom can do this. So we looked at what other metals can do, and what we found is that platinum, palladium do the same thing. These are the usual suspects for catalysis, by the way, all the expensive metals. Okay. Ruthenium, on the other hand, leaves hydrides there. Okay, that's good if I want to actually use it to maybe do hydrogenations. Having a hydride's a good thing around. It's formally H minus. You would actually put electron density onto an organic molecule. Okay, and then rhodium and iridium actually have a mixture of hydrogen negative on the formally negative on the metal atom, and H plus on the surface, which is also a potential candidate to do chemistry. In fact, it's actually the better one, because if I want to hydrogenate a polar bond, I would usually want to do a little bit of both. Okay, so what we notice, though, watch the trick, is that if we just look at the d orbital electron configuration, this is simple organometallic chemistry, the stability of whether you have a preference for having hydrides or having a hydroxyl and a hydride or just having hydroxyls really depends on the d electron count. Okay, so there's a stability issue here. We can use this then to actually say what atoms we want. We want to have some control of the ones in the middle to have maybe the hydrides and the hydroxides. This is not the only trick we're going to employ. This is one of two tricks. Here's the second trick. Okay. I mentioned that the surface can act as a reservoir of electrons that can be used to actually drive a chemical reaction. So what we discovered in the STM and in the simulations is the following. If we put hydrogen down, and we keep putting hydrogen down, so we hit this thing with a molecular beam, eventually that surface reconstruction disappears. Hit it long enough, you start seeing water coming off the surface. So you you basically start creating so many hydroxides, you start getting water forming and it leaves and you start getting edge pits. If you monitor then what's happening to the atom, the metal atom, two things happen. First of all, the charge on the metal atom goes from being positive, it goes from being a cation, to being negatively charged. And this would be whether it's palladium, platinum, or anything. So even though you're dumping electrons effectively into the surface, some of that is ending up on the metal. So I'm changing the nature of the surface, I'm changing the charge of the metal, okay? And at the same time, I look at, though, and this is the thing you gotta watch, the binding energy of the metal in that hole also starts leaving, so that you don't want to destabilize that metal because it'll sinter and form nanoparticles. So then you're not doing single atom catalyst anymore. So there's a balance there. So we have another handle. We can actually change the charge state of the metal in a very controlled way by effectively adjusting the oxide. But as I said, that oxide now can serve as a source. So here's the pieces. I need to have a partially reduced magnetite surface. I'm going to pick one of the atoms in the middle, rhodium, because I can have protons and hydrides. And I am going to actually see what happens. So this is experimental XAFs compared to our theoretical model. That is not a fit. That is a theory model from an ab initio MD simulation where we kind of compute the XAFs at every step, do an ensemble average, compared to what was measured. No adjustable parameters. Okay? So it's a good model. And I can tell you if I take an oxidized surface, it doesn't fit as well. I've got that somewhere in the backup slides. Okay, so here we go. If I try to put CO down on that surface, it will not stick. Or CO2 down on that surface, it will not stick when it's oxidized, but it binds strongly when it's reduced. And the exact opposite happens for CO. So what I can do is as I change the redox state of the surface, I know, I started late. 3 more slides, and I'll go quicker. Okay, I can flip the chemistry on this thing. And boom, that's what we see. So these are experimental measurements. The higher loadings are actually, this is the kinetics, same we showed before. These are experimental numbers. Higher states with nanoparticles, the rates are really low. The rates are actually quite high, on the order of 1 per second, which is roughly an industrial catalyst. That's what you would expect, 1 per second. Keep that number in your head. 1 per second if you do it at, on the reduced surface with a single atom, okay? And interestingly enough, this is the simplified mechanism. We've got a monster that looks like spaghetti with all these side channels. That's the main pathway. And for the first part, the rate determining step is down here, which is really taking a CO2, which is actually, in this case, bound to the metal. So it doesn't bind as a carbonate. It actually binds to the surface. You don't see a formate either. Those pathways are kind of dead ends or higher in energy. And you basically kick off a CO that way. So you first bind it as a carboxyl, then you pull off an OH. Okay, so that works. So, okay, that's a fluke. Do it again. Okay, we did it again. Completely different system. Shows the principle. So we use theory in combination with experiment. Here's TiO2, here's palladium, single atoms. This is work done by Janos Zanyi, finished off by Manthwang. We'd already left P&L at this point. And what you see is, okay, if I have the intermediate state where I have a reduced surface where I still have single atoms, I can get a relatively high rate, a little less than the magnetite. It's a little less than 1 per second. I can actually get a rate for basically turning CO2 into CO, okay? So the bottom line is we have a recipe on how to drive these catalysts there. The downside is that they start sintering into nanoparticles. On these surfaces, you have to control that, and once they form nanoparticles, the reactivity just goes way down. So the nanoparticles are actually incredibly worse at this reaction. So the point is that we can use the complexity of the system in a combination of just understanding fundamental principles to actually drive the chemistry we want. That was the goal. Okay. That's the main thing. Here's my last bit to say happy birthday to Michele. We have enjoyed the conversations over the years. I worked with him as a postdoc in MPI Stuttgart. It was a wonderful time. I learned a lot. For me, the joys of the last few years have been particular going to visit every year at one point, and just discussing the incredible science the group is doing. I've seen the talks. It's fantastic. I think you guys, what you're going to do in catalysis is going to change the future. It's really important. You know, I can only say that one of the nicest things that Michele did for me, though, was when I was, shall we say, on a run of bad luck due to a big mouth and not an ability to handle a difficult political situation. I ended up in a hard spot, and he actually helped me come here to this place, which is actually one of the greatest places in the world to do science, and I hope you all enjoy your time here. And because Michele did that, I turned my career around, and I will be ever thankful. So thank you, Michele, and happy birthday. You got to be more aggressive to get me to shut up. You know that, right?
So questions to this long and interesting talk?
I'm going to be super quick. Thanks a lot, Roger. Awesome work. Question about the D-band relationship. So that's based on the sort of nominal D-band filling that those elements should have.
Yep.
Have you actually tried to correlate it with the actual oxidation state of those metals in that condition?
Yes. Yes.
That fits the same relationship?
Yes, of course.
All right.
Roger, you can elaborate more if you want.
Why? He asked the question, I answered the question.
Okay. Another, anybody has a long question? No? I have a question myself.
You told me I went too long. I'm trying to go quick.
Yeah. Roger, when you consider the surfaces,
it gives free energy of energy. So if you go to noble metals, gold, or then the energy becomes small again.
Right. Yeah, this will not work. Well, it would actually go to 10, and it would be basically like a quarter one. You're right. So this works because these are all transition metals, and this is chemistry that have a transition metal. Okay.
It goes up and goes down.
Right. Yeah. It's a limited model. We're just trying. This is no different than basically what you would do in organometallic chemistry. Okay.
okay. Okay, let's, okay, yeah, okay. I am obliged to, so. Okay, let's thank the Roger.
Okay, there's coffee outside right now, and at 4 we start the colloquium. So, see you later. After, yeah. Yeah, there's going to be a group photo after the colloquium.